What if the world around you, everything you see, everything you touch, isn't quite real? Not in a philosophical sense, but in a physical one. We've always been taught that our universe is it, the final layer of reality. But what if it's not? What if our entire cosmos, with its trillions of galaxies, is just one part of a structure so vast and alien that we're only now finding the first clues? What if we're living inside something much, much bigger? Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This isn't science fiction. This is a story about a real scientific mystery, an anomaly so profound it has led physicists to a radical, almost terrifying conclusion. Our universe might be just a thin membrane, a single page in a cosmic book, floating in a higher dimensional space we can't see. The clues are hidden in the very fabric of reality, in the forces that govern everything. And following them leads us to the edge of what we know, where the line between our reality and another, larger one begins to blur. This is the story of the hunt for hidden dimensions, and what it would mean if we find them. The mystery starts with a force you feel every single moment of your life: gravity. It holds you to the Earth, keeps the planets in orbit, and binds entire galaxies together. It's the master force of the cosmos. And yet, when you really get down to it, gravity is weirdly weak. You overcome the gravitational pull of the entire planet Earth every time you lift your foot. Every time you pick up a cup of coffee. A simple refrigerator magnet holding up a piece of paper is winning a fight against a celestial body with a mass of 6 trillion kilograms. This isn't just a fun fact. It's a giant hole in our understanding of physics. A problem so deep it has a name. The hierarchy problem. Why is gravity trillions upon trillions of times weaker than the other fundamental forces? It's a clue. A loose thread in the tapestry of reality. And when physicists started pulling on it, the world we thought we knew began to unravel. The cracks in our reality. To get how strange gravity's weakness is, you need to meet the rest of the family. The universe runs on 4 fundamental forces. Think of them as the pillars holding up all of reality. First, there's the strong nuclear force. As the name suggests, it's titanically powerful. It's the glue that binds fundamental particles called quarks into protons and neutrons, and then holds those together inside every atom. Without it, matter would instantly fly apart. It only works over tiny distances inside an atom's nucleus, but in its domain, it's the undisputed champ. Next up is the electromagnetic force. This one's responsible for basically everything you interact with: light, electricity, magnetism, and the entire structure of atoms. It dictates all of chemistry, from a star burning to a neuron firing in your brain. And as we saw with the magnet, a tiny sliver of it can easily tell a planet's worth of gravity to take a hike. Then there's the weak nuclear force. It's less intuitive but just as vital. It governs certain types of radioactive decay and helps power our sun, allowing it to fuse hydrogen into helium. It's weaker than the strong and electromagnetic forces, but it's still immensely more powerful than gravity. And then there's gravity. The odd one out. The ghost at the party. On the cosmic scale, it rules because it has infinite range. But on the particle scale, where the other forces live, gravity is so feeble it's barely there. If you compare the electromagnetic repulsion between 2 protons to their gravitational attraction, the electromagnetic force is stronger by a factor of about 10 to the power of 40. That's a 1 with 40 zeros after it. This is the hierarchy problem. It's one of the biggest unsolved mysteries in physics. Why the huge gap? It's like having 4 siblings where 3 can lift mountains and the 4th can barely lift a feather. You'd start to suspect there's something different about that 4th sibling. Physicists have wrestled with this for decades. The Large Hadron Collider, or LHC, was built in part to hunt for new particles or theories that could explain it, but the simplest ideas have been ruled out. The mystery just got deeper. So a few physicists started asking a wilder question. What if gravity isn't weak? What if it only looks weak to us? What if it's just as strong as the other forces, but we're only feeling a tiny bit of its real power? If so, where is the rest of it going? Their proposed answer is as elegant as it is mind-bending. It's leaking away into extra dimensions. A journey into Flatland. Okay, before we plunge into hidden dimensions, we need to do some mental gymnastics. Our brains evolved in 3 spatial dimensions: length, width, and height. Forward, backward, left, right, up, down. That's our world. Trying to truly visualize a 4th spatial dimension is like trying to imagine a new color. Our 3D brains just can't do it. So, let's do what great science storytellers do and visit an imaginary world. Imagine a universe that exists only on a flat, 2-dimensional plane. Let's call it Flatland. The inhabitants of Flatland are 2D shapes: triangles, squares, circles. They have length and width, but 0 height. To them, the concepts of up and down are meaningless. Their entire reality is confined to this plane. A Flatlander scientist could work out a complete set of physical laws for their 2D universe and be totally confident they had the full picture. Now, imagine you, a 3-dimensional being, decide to visit. You exist in the bulk, the higher dimensional space that Flatland sits in. To the Flatlanders, you're completely invisible. What happens when you interact with their world? You gently lower your finger to touch their plane. From your perspective, you're just touching a surface. From their perspective, the 2D cross-section of your fingertip just materialized out of thin air. As you push your finger through, that circle grows. As you pull back, it shrinks and vanishes. To a Flatlander, this is a miracle or a terrifying violation of physics. If you were to speak, the sound waves would vibrate through their 2D world, creating a disembodied voice that comes from everywhere at once. You could peer down into their locked rooms, reach in, and move things around without ever opening the door. From their perspective, you'd be a god, performing supernatural feats just by having access to 1 extra dimension of freedom. This idea, made famous by the 1884 book Flatland, teaches us 2 huge lessons. First, creatures in a lower dimension might be totally unaware of any higher dimensions. Second, and this is the big one, a higher dimension can affect a lower one in ways that seem impossible to its inhabitants. Now, let's flip it. What if we're the Flatlanders? What if our 3D universe is just a slice, embedded in a 4D, 5D, or even 10D space? It would mean there's a cosmic up and down that we are completely blind to. And it raises a critical question. Could something from that higher dimensional bulk be interacting with our universe right now? Suddenly, the weakness of gravity doesn't look like a problem. It looks like evidence. The first clue: Kaluza's hidden world. The idea of extra dimensions isn't new. The first serious scientific proposal came way back in 1919 from a mathematician named Theodor Kaluza. It was just a few years after Einstein had published his masterpiece, The Theory of General Relativity, which describes gravity as the curvature of space-time. At the time, the only other known force was electromagnetism, described by a totally separate set of equations. Kaluza wondered if they had to be separate. He decided to play a mathematical game. He took Einstein's equations for our three-space and one-time dimension universe and rewrote them for a universe with one extra spatial dimension. He crunched the numbers, and what he found was mind-blowing. Out of the math for a five-dimensional universe popped the original equations for gravity, just as expected. But he got something else, too. An extra set of equations emerged, uninvited. When Kaluza looked at them, he realized he'd seen them before. They were Maxwell's equations for electromagnetism. By simply adding a fifth dimension to gravity, the theory of light appeared automatically. It suggested that gravity and electromagnetism weren't separate forces at all, but two sides of the same coin. Geometry in 5 dimensions. He sent his paper to Einstein, who was floored, writing back, "At first glance, I like your idea enormously. But there was one glaring problem. If this fifth dimension is real, where is it?" A few years later, in 1926, a physicist named Oscar Klein added a brilliant twist. He proposed that the fifth dimension is real, but it's not big and expansive like ours. Instead, it's curled up into a tiny, tiny circle at every single point in space. Imagine a garden hose. From far away, it looks like a 1D line. But up close, you see it has a second dimension. Its circumference. Klein argued the fifth dimension was like that, but curled up to a size far smaller than an atom, so we could never see or enter it. This Kaluza-Klein theory was beautiful. It unified the two known forces through pure geometry. But it didn't hold up. When the strong and weak nuclear forces were discovered, there was no simple way to fit them into the model. Worse, the theory predicted new particles that were never found and made other predictions that just didn't match reality. For decades, the idea of extra dimensions was shelved as a clever dead end. But it planted a seed. Maybe forces that look different in our world are just geometry in higher dimensions. The idea wasn't wrong, it was just incomplete. It would just take another 70 years to figure out how to use it. The universe as a bubble. The brainworld revolution. Fast forward to the late 1990s, and the hierarchy problem was a full-blown crisis. At the same time, string theory had become a leading candidate for a theory of everything. It proposes that everything is made of tiny, vibrating strings. But for the math to work, string theory needed the universe to have 10 dimensions. Suddenly, extra dimensions were back. At first, everyone assumed they must all be curled up and tiny, like Klein suggested. But then, a few groups of physicists Arkani-Hammond, Dimopoulos, and Diwali, and then Randall and Sundrum proposed a totally new, mind-bending idea. What if not all the extra dimensions are small? What if some are huge, maybe even infinite? And what if the reason we don't see them isn't because they're tiny, but because we are trapped? This is the *brainworld* scenario. The name comes from membrane. In this model, our entire 3D universe is just a 3D brane, a surface floating inside a higher dimensional space called the bulk. All the stuff of our universe, protons, electrons, photons, the strong and weak forces, are stuck to this brane. We can move anywhere we want on the brane, but we can't leave it. But, the theory says, there's one exception. Gravity. The particle that carries gravity, the graviton, is different. It's a closed loop, with no ends to get stuck on the brane. It's free to travel anywhere, including off our brane and into the bulk. And just like that, the hierarchy problem is solved. Gravity isn't weak. It's incredibly strong. We just feel a tiny, diluted fraction of it. Most of its strength leaks away from our universe, spreading out into the extra dimensions. It's like standing in the corner of a giant warehouse with a single, powerful light bulb in the center. You only get a tiny fraction of its light because it has spread out over a huge volume. The other forces are stuck to our brane, so their strength is concentrated right here with us. But gravity's influence is diluted across the entire, massive bulk. To us, it just looks feeble. Its weakness is an illusion of geometry. The implications are just staggering. It means that millimeters away from you, in a direction you can't point, there could be a vast, higher dimensional reality. Our universe might be just one of many branes floating in the bulk, like soap bubbles in the air. Parallel universes. Most of the time, these worlds would be undetectable. Their light can't reach us. But gravity, the one force that can travel between branes, could be a messenger. Some have even wondered if dark matter is just the gravitational shadow of matter on a nearby, parallel brane. What about the Big Bang? In this model, it wasn't a singularity. It was a cosmic car crash, the collision of two parent branes floating through hyperspace. The colossal energy of that impact created the hot, dense fireball that started our universe. This isn't just a fun story. It's a testable hypothesis. If it's true, it should leave clues we can find. Searching for shadows of other dimensions. Okay, that's a great story. But is there any way to prove it? It sounds untestable, but it's not. The braneworld scenario makes real predictions we can check at the Large Hadron Collider. The LHC smashes protons together at insane speeds to see what comes out. So how do you find an extra dimension in the wreckage? You look for things that just vanish. If a collision at the LHC is energetic enough, it could create a graviton. And if that graviton is free to roam the bulk, it can get kicked right out of our universe, taking its energy and momentum with it. From our perspective, we'd see a crime against physics. Energy and momentum disappearing into thin air. Experiments at the LHC look for a monojet, a single spray of particles shooting off in one direction, recoiling against. Well, nothing. That nothing would be the graviton that just noped out of our universe. It would be the smoking gun. So, did we find it? So far, nope. After sifting through countless collisions, there's no definitive evidence. This doesn't kill the theory, but it means if these dimensions exist, they're harder to access than we first hoped. There's another, even wilder prediction. Tiny black holes. In our 3D world, you can't make a black hole at the LHC. But if extra dimensions are real, gravity gets much stronger at very short distances. Strong enough that two colliding protons could briefly collapse into a microscopic black hole right there in the detector. Now, that sounds terrifying. But it's totally safe. These tiny black holes would evaporate almost instantly in a unique puff of particles called Hawking radiation. It's another key signal they're looking for. And again, the search has come up empty. The trail seemed to go cold. But the lack of simple answers has forced physicists to think harder. Maybe the influence of extra dimensions isn't about leakage. Maybe it's something woven more deeply into the very nature of reality. The deepest layer of the mystery, geometry, creates mass. For years, we thought we had the origin of mass figured out, the Higgs field. It's an invisible energy field that permeates space, and particles get their mass by how much they stick to it. The discovery of the Higgs boson in 2012 confirmed this and was a huge triumph. But it's not the whole story. The theory doesn't explain why the Higgs field is there. To some, it feels tacked on. This is where things get really cutting edge. A recent paper in Nuclear Physics B*, led by physicist Richard Pinsick, proposes something radical. It suggests we might not need the Higgs field at all. Instead, mass could come directly from the geometry of hidden dimensions. As Pinsick puts it, matter emerges from the resistance of geometry itself, not from an external field. To get this, we have to go back to M-theory, which says our universe has 11 dimensions. The 7 extra dimensions are curled up into a complex, 7-dimensional shape called a *G2 manifold. Think of it as an incredibly intricate piece of cosmic origami existing at every point in space, too small to see. Pinsick and his team modeled this shape not as a static backdrop, but as something dynamic. They found these shapes can have a property called torsion, a kind of built-in, geometric twist. As Pinsick explains, as in organic systems, such as the twisting of DNA, these extra-dimensional structures can possess torsion. Their model shows that this 7D shape would naturally settle into a stable, twisted configuration. And this twist in the hidden geometry would be felt by particles in our world as resistance. This geometric resistance would look to us exactly like mass. The math works out to mimic the Higgs mechanism, but it comes from the pure geometry of reality itself. This is a huge shift. It suggests the properties of matter aren't random. They're a direct result of the shape of unseen dimensions. Geometry is destiny. And this theory makes a wild new prediction. Just like you can pluck the Higgs field to create a Higgs boson, you should be able to pluck this geometric field to create a new particle. The team has a name for it. The torstone. The torstone would be a ripple in the fabric of 7-dimensional geometry. Finding it perhaps through tiny anomalies in collider data or gravitational waves would be direct physical evidence that mass itself is an echo from a hidden world. The theory even hints that this geometry could be linked to dark energy, the mysterious force causing the universe to expand faster and faster. The terrifying and awe-inspiring consequences. So where does this all leave us? We're standing on the edge of a cliff, staring into a whole new reality. If any of this is true, the consequences are profound. The brainworld shatters our cosmic solitude. We could be one of countless bubble universes in a vast multiverse. The question is no longer, are we alone in the universe? But, is our universe alone? The idea of a higher dimensional being becomes scientifically plausible. A creature in the bulk would be to us what we are to a Flatlander, a god, or a monster. They could see everything about us, step in and out of our reality at will, and perform acts that look like miracles. Are we living in a cosmic nature preserve, being watched by things we can't comprehend? The geometry creates mass idea is even more unsettling. It implies our reality is a shadow play. The things we think are most fundamental like mass and substance aren't real. They're just effects, borrowed from a geometric structure we can never touch. It's Plato's cave on a cosmic scale. We are prisoners, building our science based on shadows, while the true reality remains forever outside our cave. And yet, there's a stunning beauty in this. It suggests a universe of incredible elegance. Gravity, light, the nuclear forces, even mass itself all could be different notes in a single, underlying geometric symphony. This quest is the ultimate expression of our drive to understand where we fit in. We keep getting demoted. We're not the center of the solar system, which isn't the center of the galaxy, which is just one of billions. And now, our entire universe might not even be the final layer of reality. But this shouldn't make us feel small. It should fill us with wonder. It means the map is still mostly blank, and the greatest discoveries may still be waiting in the shadows, just beyond our sight. It all started with a refrigerator magnet winning a fight against an entire planet. That one simple fact, the absurd weakness of gravity, has forced us down a rabbit hole. It's led us to question the number of dimensions, to picture our cosmos as a bubble, and to wonder if matter itself is just a phantom of hidden geometry. we don't have the final answer. We've found no definitive proof, no missing energy, no micro black holes, no torstones. But the search has changed what we think is possible. These are testable, scientific theories being pursued by thousands of the world's brightest minds. Whether our universe is all there is, or just a single note in a vast, multidimensional symphony, the quest to find out is one of the most important adventures we've ever undertaken. The world around you feels solid. Your reality feels complete. But the clues are there for those brave enough to look. We are cosmic detectives, and the ultimate revelation might be that our universe, our home, is just the beginning. The search for a deeper understanding of our universe is something we all do together. If these ideas sparked your curiosity, share this with someone who'd appreciate it. What do you think lies beyond our 3 dimensions? Let us know in the comments. And for more journeys into the deepest mysteries of the cosmos, make sure you subscribe. The universe is full of secrets, and we're just getting started. Science's terrifying new map of what's outside the universe. We all have a picture in our heads of the Big Bang. A tiny, hot, dense point that exploded. From there, the fabric of our universe started expanding like a balloon, inflating into a vast, empty nothingness. We see those familiar images of galaxies rushing away from us, and we're told this is the story of how it all began. But what if that picture is wrong? The truth is, on the absolute frontiers of physics, the latest maps of reality suggest something far more bizarre and unsettling. They suggest our universe isn't expanding into emptiness at all. Because there might not be any emptiness for it to expand into. Instead, our entire reality, every star, every galaxy, every atom in your body might just be a thin membrane, a single slice of existence, floating in a higher dimensional space we cannot see, touch, or even begin to comprehend. And what's lurking in that higher dimensional, outside, could be grander and more alien than we have ever dared to imagine. This isn't just a late-night thought experiment. This is a potential description of reality. And today, we journey to the edge of the known to explore science's terrifying new map of what might lie outside the universe. The old picture and its cracks. To understand where we might be going, we first have to get a handle on where we are. The standard story of our universe, our current map, is one of the greatest achievements in human history. It all starts 13.8 billion years ago with the Big Bang. Now, most people imagine this as an explosion happening in space, like a bomb going off in a dark, empty room. That's not quite right. The Big Bang happened everywhere at once. It was the birth of space and time itself. The universe isn't expanding with galaxies flying through space. It's space itself that's stretching between them, carrying them apart like raisins in a rising loaf of bread. This model, called the Lambda CDM model, is spectacularly successful. It predicted the cosmic microwave background, the faint, leftover heat from the Big Bang, with incredible accuracy. It explains the cosmic web, the large-scale structure of galaxies and the vast voids between them. It's built on 2 pillars of 20th-century physics. Einstein's general relativity, which describes gravity as the shape of space-time, and the standard model of particle physics, which describes everything else. The standard model is, without a doubt, the most successful and precisely tested scientific theory we've ever come up with. It describes the 3 other fundamental forces: the strong force binding atoms together, the weak force governing radioactivity, and the electromagnetic force that rules light, chemistry, and electricity. For 50 years, it has survived every single test we've thrown at it. But this beautiful picture has cracks. Deep, fundamental cracks that point to something we're completely missing. And the most glaring of these, the one that keeps physicists awake at night, has a name: the hierarchy problem. And it all starts with something you can test in your own kitchen. Take a simple fridge magnet. This tiny piece of metal can pin a piece of paper to your refrigerator door, effortlessly defying the entire gravitational pull of the planet Earth. A planet with a mass of nearly 6 trillion kilograms is being beaten by a magnet that weighs a few grams. Think about how insane that is. This shouldn't be possible. Of the four fundamental forces, gravity is, by a staggering margin, the weakest. And not just a little weaker. It's ridiculously, absurdly feeble. The electromagnetic force between two protons is roughly a 1, followed by 36 zeros times stronger than their gravitational pull. If the electromagnetic force were the size of the entire known universe, the gravitational force between those same two particles would be smaller than a single atom. This massive discrepancy is the hierarchy problem. Why is there such a ridiculous gap between gravity and the other forces? Nature doesn't usually do things in such an arbitrary way. The other forces, while different, play in the same ballpark. But gravity is the outcast, weaker by orders of magnitude that are hard to even wrap your head around. According to our best theories, it shouldn't be this way. The fundamental properties of the universe that give rise to mass and gravity should be closely connected. Quantum mechanics tells us they should be pulled together. Instead, they're separated by a chasm of 17 orders of magnitude. For that to be true, the numbers that define our universe would have to be fine-tuned to an impossible degree of precision. It's like balancing a pencil on its sharpest point and having it stay perfectly still for 14 billion years. Physicists hate fine-tuning. It feels like cheating. It suggests our theories are missing a huge piece of the puzzle. The hierarchy problem is a giant, flashing neon sign pointing to a massive hole in how we see the universe. It tells us that either our understanding of gravity is profoundly wrong, or there's some hidden physics, some secret mechanism, that's making gravity appear this weak. And the search for that new physics has led scientists to a new, and terrifying, map of reality. Introducing the new map. Brins and the bulk. To even begin to read this new map, you have to challenge your most basic idea of space. We live in 3 spatial dimensions: length, width, and height plus time. But what if that's just a sliver of the whole picture? This idea isn't actually new. Back in the 1920s, a physicist named Theodore Kaluza had a wild thought. What would happen if you wrote down Einstein's equations for gravity not in our normal 4 dimensions, but in 5? The result was mind-blowing. Out popped not just Einstein's theory of gravity, but also the equations for electromagnetism. It was as if a 5th, hidden dimension magically unified gravity and light. But if it exists, where is it? His colleague, Oscar Klein, suggested it was curled up into a tiny circle, so small we could never see it. Imagine a tightrope walker on a wire. From far away, the wire is just a one-dimensional line. The walker can only move forward and backward. But for an ant on that same wire, there's a second dimension. It can crawl around the circumference. Kaluza and Klein imagined that at every single point in our space, there's a tiny, curled-up dimension just like that. For decades, this was a mathematical party trick. Then came string theory. In the 1980s, physicists trying to unite gravity and quantum mechanics proposed that everything is made of tiny, vibrating strings. Different vibrations of these strings look like different particles. One vibration pattern is an electron, another is a photon, and another is the graviton, the hypothetical particle of gravity. But for the math to work, string theory needed a shocking ingredient. Not 4, but 10 dimensions. So, where are the other 6? Physicists dusted off the Kaluza-Klein idea, suggesting they're all curled up into some complex, microscopic shape at every point in space. This was the accepted picture for a while. But in the 1990s, a new, even more radical idea emerged from something called M-theory. This update, which works in 11 dimensions, introduced new things to the cosmic zoo. Not just tiny strings, but higher dimensional objects called branes, short for membranes. This is where the map gets really strange. This new concept, called brane cosmology, suggests that the extra dimensions might not be small and curled up at all. They could be huge, maybe even infinite. So why don't we see them? Because, the theory goes, we are stuck on a brane. Imagine a single, vast, three-dimensional sheet floating in a higher dimensional space. Everything that makes up our world, electrons, quarks, photons, you, me, the Earth, and every star is stuck to this sheet. These particles and forces can move around in our three dimensions, but they can't leave. Our entire universe is confined to this three brane. This higher dimensional space that our brane floats in is called the bulk. And just like that, we have a possible and breathtakingly elegant solution to the hierarchy problem. Why is gravity so weak? Because gravity isn't stuck to the brane. In this model, the strong, weak, and electromagnetic forces are confined to our three brane. But gravity isn't. It is free to spread out through all the dimensions, our own and the vast dimensions of the bulk. Think of it like this. If you shout in a small, sealed room, the sound is loud and concentrated. If you shout in a giant, open field, the sound spreads out, becoming much fainter with distance. According to brane cosmology, the other forces are shouting in our sealed room. Their strength is trapped here with us. But gravity's strength is diluted. It leaks out from our brane into the immense emptiness of the bulk. We only feel a tiny fraction of gravity's true power. The reason your fridge magnet can defy a whole planet is because most of gravity's force isn't even in our universe. It's lost to the bulk. This idea doesn't just solve the hierarchy problem. It completely reframes our existence. Our universe isn't everything. It's a slice, a surface, and it's floating in something much, much bigger. Exploring the terrifying implications. If we live on a brane floating in a higher dimensional bulk, the consequences are dizzying. This isn't just abstract math, it's a new blueprint for the cosmos, with implications that feel almost theological. First, let's think about the Big Bang. The Standard Model says the universe began from a singularity, a point of infinite density where our laws of physics just stop working. It can't tell us what came before the Big Bang, because time itself supposedly began there. Brane cosmology offers a wild alternative. What if the Big Bang wasn't the beginning? What if it was just a violent event in an ongoing timeline? This is the core idea of the ekpyrotic universe model. Ekpyrotic comes from an ancient Greek word for a cyclical, fiery rebirth of the cosmos. In this modern version, our universe isn't the only brane. There could be countless parallel universes, all floating like cosmic sheets in the higher dimensional bulk. And these branes can move. Sometimes they might collide. According to this model, the Big Bang wasn't an explosion from nothing, but the cataclysmic collision of two parallel branes. Imagine two immense cosmic sheets drifting toward each other over eons. The moment of impact releases an unimaginable blast of energy, heating our brane to trillions of degrees and creating all the matter and radiation we see. This Big Bang is less of a bang and more of a bounce. The collision kickstarts the expansion of our universe as the branes rebound. Now, it's important to say that this is a speculative alternative to the more accepted theory of cosmic inflation. But it solves many of the same puzzles without needing a singularity, that point where our physics breaks. It also opens up a profound possibility. This may have happened before, and it might happen again in an endless cycle of cosmic death and rebirth. Could we ever find evidence for such a cosmic fender bender? Maybe. In our baby picture of the universe, the cosmic microwave background, there's a baffling anomaly known as the CMB cold spot. It's a region of the sky that's unusually large and colder than it should be. One leading explanation is that there's a massive supervoid between us and the CMB, a vast region with less matter that cools the light passing through it. But several studies have found that the voids we can see don't fully account for how cold it is. This has left the door open for more exotic ideas. One is that the cold spot is a scar, a cosmic bruise, the lingering remnant of a collision between our brane and another universe, long ago. While this is highly speculative and the data is nowhere near proof, it's a tantalizing hint that we might be seeing the first echo of another world. The other implications are even more personal. If we're creatures stuck to a 3 brane, our entire perception of reality is fundamentally limited. We're like the characters in the famous 19th century story Flatland. A Flatlander, living on a 2D plane, has no concept of up or down. If a 3D sphere passed through their world, they wouldn't see a sphere. They'd see a point appear from nowhere, grow into a circle, then shrink back to a point and vanish. It would be a bizarre, inexplicable miracle. Now, apply that logic to us. What if a 4D being from the bulk were to interact with our world? We wouldn't see a 4D being. We might see objects appearing and disappearing out of thin air. Events with no cause. A being with access to a fourth spatial dimension could see inside our locked rooms, see every part of our bodies inside and out at the same time. It could pluck an object from a locked safe without opening the door, just by lifting it up into the fourth dimension and putting it back down. Its power over us would be like our power over a character on a page. The sense of existential vertigo is immense. This leads to one of the most mind-bending ideas in physics, the holographic principle. It was inspired by studying black holes, where scientists discovered that the information for a 3D object can be encoded on its 2D surface. The holographic principle asks, what if this is true for the whole universe? It suggests our 3D reality is just a projection, a hologram. The real physics might be happening on a distant, lower dimensional boundary, and everything we experience is just a projection of that information. In this context, our 3 brane could be a holographic projection of physics happening in the bulk. What we perceive as solid reality may just be a lower dimensional message, written in a language we're only just starting to understand. The search for evidence. These are profound ideas leaking gravity, colliding universes, holographic realities. But is it science, or just fascinating philosophy? The answer is, it's testable. As strange as they sound, these theories make predictions we can look for. And for the last 2 decades, that's exactly what physicists have been doing. The most direct way to find extra dimensions is to try and send something into them. This is one of the key missions of the Large Hadron Collider, LHC, at CERN. If large extra dimensions are real, the LHC might spot them in a few ways. One signature is missing energy. When particles collide, detectors see the debris fly out. Energy in equals energy out. But if a collision creates gravitons that can leak into the bulk, they would simply vanish from our detectors, carrying energy with them. We'd see a shower of particles recoiling against nothing. Another sign would be creating tiny, microscopic black holes. Gravity is normally too weak for this, but if it gets much stronger in extra dimensions at tiny distances, 2 colliding protons could briefly form a mini black hole, which would instantly evaporate in a spectacular burst of particles. So, after years of operation and trillions upon trillions of collisions, what has the LHC found? A striking, profound silence. As of early 2026, no definitive evidence for large extra dimensions, graviton leakage, or micro black holes has been found. This null result is a vital piece of science. It has ruled out many of the simplest models and forced theorists to refine their ideas. If extra dimensions exist, they must be smaller or more complex than we first hoped. But the hunt is far from over. A new tool has joined the search: gravitational wave astronomy. Observatories like LIGO and Virgo detect ripples in spacetime itself. If gravity leaks into extra dimensions, it could cause tiny, specific distortions in these waves as they travel toward us. So far, the measurements align with Einstein's 3+1-dimensional theory, putting tight constraints on some extra-dimensional models, but the search continues with increasing precision. And of course, scientists are still scouring the cosmic microwave background, looking for more anomalies that might hint at a time before the Big Bang or the influence of other branes. All of these theories remain on the speculative edge of physics. The lack of evidence from the LHC has been a major reality check. This is how science works. A slow, careful process of pushing into the dark, ruling out what isn't there, and patiently waiting for a flicker of light from the unknown. We started with a simple picture of the universe: a balloon expanding into nothing. We end with something far stranger: a new map. One that suggests our universe could be a delicate membrane floating in a vast, higher-dimensional sea. A map where the Big Bang might be the echo of a cosmic collision, and where our solid reality could be a mere holographic projection. The central mystery we started with, the inexplicable weakness of gravity, finds a mind-bendingly elegant solution in this new picture. Gravity isn't weak, it's just spread thin, its power diluted across dimensions we can never hope to see. This map is terrifying because it shatters our sense of completeness. It suggests our universe is not the universe, but just a tiny part of a much larger, and infinitely more complex, reality. It gives you that feeling of a flatlander suddenly being told about, up. But it is also a map filled with awe. It tells us that what we perceive might be only a sliver of the whole story. It opens the door to possibilities we're just beginning to imagine: parallel worlds, higher dimensions, and a cosmos more intricate and mysterious than anyone could have ever conceived. The search for proof continues, in the heart of particle colliders and in the oldest light in the universe. We don't have the answers yet. We are still drawing the coastlines on this new, terrifying map. But one thing seems certain: the universe is not what it seems. And the quest to find our true place within it is the greatest adventure of all. The old map is obsolete. The journey into the bulk has begun. Our universe is a bubble inside a multiverse. Imagine you're looking at a perfectly flat map of the world. From your point of view, that's the whole story. It has 2 dimensions, length and width, and that is it. It's a complete, self-contained reality. Then one day, something impossible happens. A single, tiny point appears out of nowhere. And in total defiance of logic, that point starts to grow, stretching into a line. The line expands, moment by moment, then just as bizarrely, it shrinks, collapses back into a point, and vanishes as if it were never there. What you just witnessed, from your 2-dimensional world, is a 3-dimensional sphere passing through your reality. You can't see the whole sphere, of course. Your senses aren't built for it. You can only see the slice of it that intersects with your flat world. So, here's a question that might keep you up tonight. What if our entire, vast, 3-dimensional universe is just like that flat map? And what if a 4-dimensional sphere is about to pass through it? What would we see? A point, appearing in the void, which then swells into a sphere. One that grows to an unimaginable size before shrinking back to nothing and disappearing forever. No warning. No escape. This isn't just a thought experiment. This is a real possibility that comes from some of the most profound and mind-bending ideas in modern physics: the idea that our universe is not all there is. That it might be a fragile membrane, a bubble, floating in a vast, higher dimensional ocean. We are about to journey to the very edge of reality, into a world of hidden dimensions and cosmic collisions. We're going to explore a stunning theory, born from the cutting edge of string theory, that says our universe is just one of many, a single bubble in a multiverse of possibilities. By the end of this, the familiar night sky is going to look very, very different. The illusion of 3 dimensions. To really get our heads around the scale of this, we first need to rewire our brains to think about dimensions. And the best way to do that is with a story. Back in 1884, a writer named Edwin Abbott wrote a little book that has become essential reading for anyone trying to visualize the impossible. It's called Flatland, a romance of many dimensions. His world is a 2-dimensional plane. Its people are geometric shapes, lines, triangles, squares, and circles who live and move on this flat surface, with absolutely no concept of up or down. A citizen of Flatland, let's say a square, sees his world in a very limited way. When he looks at other people, he doesn't see their full shape. He just sees lines of different lengths and brightness. His entire reality is locked in 2 dimensions. To him, the idea of a 3rd dimension isn't just wrong, it's gibberish. It's a direction that simply doesn't exist. Now, imagine you, a 3-dimensional being, decide to visit Flatland. You are, for all practical purposes, a god. You can see their entire world at a single glance, the inside of their locked houses, the stuff in their pockets. They have no secrets from you because they have no way to hide anything in a direction you can see, and they can't. If you were to speak, your voice would seem to come from inside their own bodies, a terrifying, impossible event. But things get truly weird when you decide to physically enter their world. As we talked about, if you slowly lower your finger through their plane, they would witness what looks like a miracle. A point materializes from thin air. It expands into a small circle, grows to the full width of your finger, then shrinks back down to a point before vanishing completely. To the Flatlanders, this is some shape-shifting monster that appears and disappears at will. They can't possibly grasp the solid, stable, 3-dimensional structure of your finger existing just above them in that impossible 3rd dimension. The square in the story is visited by a sphere who tries to explain this. The square, naturally, can't get it. He can't point up. There's no up to point to. It's only when the sphere yanks him out of Flatland and into our 3-dimensional spaceland that his mind is finally blown open. He sees his world for what it is. Just one slice of a much bigger reality. This isn't just a cute story. It's a powerful tool for building intuition. Now, scale it up. We are the Flatlanders. Our universe, with its 3 spatial dimensions, length, width, and height, is our Flatland. Every direction we can point, every move we can make, is just a mix of X, Y, and Z. But what if there's another axis? A 4th spatial dimension, let's call it W, that's perpendicular to the other 3 in a way we can't gesture towards or even properly imagine. Just like up is nonsense for a Flatlander, this 4th direction is nonsense for us. If a 4-dimensional being existed, it would have that same god-like view of us. It could see the inside of a locked bank vault as easily as we see a square drawn on paper. It could look inside our bodies and watch our organs work from a perspective we can't fathom. And if a 4-dimensional object, a hypersphere, passed through our 3D space, we'd see that same impossible event. A point appearing from nowhere, swelling into a sphere of colossal size, then shrinking and vanishing without a trace. It would be a cosmic event on an unimaginable scale, looking like it's coming from everywhere at once, and there'd be nothing we could do. A simple physical event in 4 dimensions would be a terrifying, physics-breaking miracle in ours. This single thought flips our entire understanding of the cosmos. It suggests that what we call the universe might be just our little slice of a much grander, higher dimensional reality we're completely blind to. And this isn't just philosophy. String theory, one of the top candidates for a theory of everything, actually requires these extra dimensions for the math to work. According to the theory, our universe isn't just sitting in these dimensions. It's a very specific object living inside them. Welcome to the bulk. For decades, physicists have been trying to connect the two pillars of modern science. Einstein's general relativity, which describes gravity and the huge scale of the cosmos, and quantum mechanics, which describes the bizarre world of tiny particles. The math just refuses to cooperate. But then a framework emerged that offered a tantalizing, if completely wild, solution. String theory. String theory says that the fundamental bits of reality aren't little points, but tiny, one-dimensional vibrating strings of energy. Different vibrations of these strings produce all the different particles we see, from electrons to photons. But for the theory's equations to make any sense, it demands something extraordinary. The universe has to have more than the 3 spatial dimensions we know. Depending on which version of the theory you're looking at, it could be 9, 10, or even 11 dimensions in total. This immediately brings up a huge question. If these extra dimensions are real, where are they? We can move left, right, forward, backward, up, down. Why can't we move in those other directions? The first guess was something called compactification. Think of a garden hose from far away. It looks like a one-dimensional line. But as you get closer, you see it has a second dimension. The little circle you could walk around. The idea was that these extra dimensions are curled up on themselves, rolled into a fantastically tiny shape, trillions of times smaller than an atom. They exist everywhere, but they're so small we could never notice them. But then, a new, even more radical idea came out of M-theory, the most complete version of string theory. It's called *brane cosmology. Brane comes from the word membrane, and it's a physical object that can have any number of dimensions. A point is a 0 brane. A string is a 1 brane. A sheet of paper is a 2 brane. And according to this theory, our entire 3-dimensional universe could be a 3 brane. Picture a vast, dark, empty space. This represents the full, higher dimensional reality, which physicists call the bulk. Now, picture a single, gigantic soap bubble floating in the middle of it. The thin, 2D surface of that bubble is a universe. Our universe. We are living on the surface of this bubble, this 3 brane. All the particles that make up you, me, the Earth, the stars, they're all essentially open-ended strings whose ends are permanently stuck to our brane, trapping them here. We can move anywhere we want along the surface of the bubble, in our 3 dimensions, but we can't leave it. We are stuck to the brane. This simple, beautiful picture gives a revolutionary answer to why we don't see the extra dimensions. They aren't necessarily tiny. They could be enormous. We just can't get to them because matter and light are glued to our brane. But there is one fundamental force that, according to the theory, is not stuck. Gravity. In this model, gravity is made of closed loops of string. Unlike the open strings of matter, these closed loops aren't tied down. They are free to travel throughout the entire higher dimensional bulk. This leads to a potential solution for one of physics' longest-standing puzzles, the hierarchy problem. The question is simple. Why is gravity so incredibly weak compared to the other forces? A little refrigerator magnet can lift a paperclip, its tiny electromagnetic force easily beating the gravitational pull of the entire planet Earth. Brane theory suggests an answer. Gravity isn't actually weak. It's just as strong as the other forces. But because its messenger particle, the graviton, can leak out from our brane and spread into the vastness of the bulk, its strength gets diluted. Only a tiny fraction of its true power is felt in our 3D universe. It's like shouting in a huge, open field. Close by, your voice is strong, but far away, it's faint because the sound has spread out. Our universe only feels the distant whisper of gravity's true shout. The most famous version of this is the Randall-Sundrum model, proposed back in 1999. It describes a universe with 5 dimensions where our 3 brane is embedded in a warped or curved geometry. This warped spacetime makes gravity exponentially weaker on our brane than on another, hypothetical parallel brane. The very shape of the bulk creates the hierarchy of forces we see. This wasn't just a story. It was a mathematically sound model that solved a major problem in physics by suggesting we live on a membrane in a 5-dimensional universe. The implications are staggering. It reframes our entire existence. The cosmic expansion we see, the fact that galaxies are flying away from each other, might not just be our space stretching. It could be our entire brane universe moving and expanding within the bulk. The laws of physics we know might just be the local rules for our particular membrane. And, most chillingly, we might not be alone in the bulk. Floating just out of sight, in that unreachable higher dimension, could be other bubbles. Other universes. The birth of a universe. The standard story of our universe's beginning is the Big Bang. A moment of infinite density and heat, a singularity from which space and time exploded into being. But it leaves us with nagging questions. What was there before the Big Bang? What lit the fuse? Cosmic inflation offers some answers but still leaves us with that ultimate, mysterious beginning. Brane cosmology, however, tells a breathtakingly different story. It suggests our Big Bang wasn't a beginning at all, but simply an asterisk event. A violent, universe-creating event, yes, but one that happened in a pre-existing, timeless arena. This alternative is called the asterisk ekpyrotic model. Ekpyrosis is a word from ancient Greek philosophy meaning conflagration, or coming out of fire, part of an eternal cycle of fiery destruction and rebirth. In this scenario, our universe, our 3 brane, isn't the only one floating in the bulk. There's at least one other, existing parallel to ours, like 2 infinite sheets hanging in a dark room. For eons, these branes can be cold, dark, and empty, drifting slowly toward each other through the 5th dimension, pulled together by gravity. The moments before they hit would be completely silent and invisible to anyone living on the branes. It would be the ultimate sneak attack. Then, they collide. This isn't a crash like 2 cars hitting. This is a collision of realities. The immense energy from this impact is converted, almost instantly, into a firestorm of matter and radiation, creating a hot, dense state across the entire brane. That moment, that bang, is what we perceive as the Big Bang. From that searing hot plasma, the universe expands and cools. Particles form. Atoms emerge. Stars and galaxies begin to take shape. The universe we know is born from the ashes of this cosmic cataclysm. What's powerful about the ekpyrotic model is how neatly it seems to solve some of the Big Bang's biggest problems without needing inflation. Take the flatness problem. Our universe appears to be geometrically flat, which is a very specific and unlikely starting condition. The ekpyrotic model says that the branes, before they collide, are already nearly flat, since that's their lowest energy state. So the collision naturally produces a flat universe. Then there's the horizon problem. Why is the afterglow of the Big Bang, the cosmic microwave background, so incredibly uniform in temperature everywhere we look? Regions of the sky billions of light years apart couldn't possibly have been in contact to even out their temperatures. The ekpyrotic model explains this by the nature of the collision itself. The 2 branes are almost perfectly parallel, so they collide at almost the exact same time everywhere, creating a uniform temperature right from the start. But the universe isn't perfectly uniform. There are tiny temperature fluctuations that acted as seeds for galaxies. Where did they come from? The model has an answer for that, too. Before the branes collide, they aren't perfectly smooth. Quantum mechanics says they should have tiny ripples on their surfaces. This means they don't hit everywhere at the exact same instant. Some rippling parts touch a fraction of a second before others. These tiny timing differences lead to slightly different temperatures across the brane, creating the exact kind of primordial fluctuations we see in the sky today. So what happens after the bang? The universe expands, cools, and grows darker. Dark energy, that mysterious force pushing our expansion to accelerate, could be the lingering effect of the branes pulling apart again. For trillions of years, the branes might drift away, our universe growing cold and empty. But the cycle may not be over. Eventually, the forces between them could pull them back together once more, leading to another collision, another fire, another Big Bang. A cosmic rebirth. This transforms the Big Bang from a one-time miracle into a recurring, natural event in an eternal, oscillating cosmos. Our universe is just one chapter in an endless book. It also makes the multiverse a very concrete idea. The bulk becomes a cosmic ocean, a foam of countless brane universes. Some might be ancient and dying, others young like ours. Some might have gone through trillions of cycles. And maybe, just maybe, some could have different physical laws, born from collisions with different energies. Our universe is demoted from being all of existence to just one island in an infinite archipelago of worlds. The geometry of the strange. Our three-dimensional brains have a deep, intuitive feel for geometry. We know how spheres work, how cubes fit together, how distance feels. But if our universe is a brane floating in a higher dimensional bulk, that bulk space could play by a set of rules so bizarre they would shatter our every intuition. The geometry of higher dimensions is a place of beautiful, mind-melting strangeness. Let's start with a sphere. In our 3D world, as a sphere's radius gets bigger, its volume grows by the cube of that radius. It's a simple relationship. But what happens to the volume of a hypersphere, a sphere in higher dimensions, if you keep its radius fixed at 1 but keep adding dimensions? You might think the volume just gets bigger and bigger forever. You would be wrong. The volume of a unit sphere actually increases as you go from 1D to 2D to 3D, hitting a peak around the 5th dimension. After that, something totally bizarre happens. The volume starts to decrease. As you keep adding dimensions 6, 7, 20, 100, the volume of the hypersphere plummets, heading towards 0. A sphere in 1,000 dimensions with a radius of 1 has almost no volume at all. All of its stuff is concentrated on its surface, its skin. The inside is almost totally empty. This means in a very high-dimensional space, objects would be mostly surface. All the action is happening on the boundary, which sounds an awful lot like our universe being a boundary, a brane. The weirdness doesn't stop there. Think about packing spheres. In 2D, you can get a maximum of 6 circles to all touch a central circle. In 3D, we can manage 12 spheres touching a central one, and we think that's the limit. But when you go to higher dimensions, the rules go haywire. In 8 dimensions, you can fit 240 spheres around a central one. In 24 dimensions, you can fit a mind-boggling 196, 560. The ways objects can interact in higher dimensions are vastly more complex than in our world. Now for the real head-scratcher. The cube. Imagine a 3D cube. You can fit a sphere perfectly inside it, touching all 6 faces. Now, let's go to higher dimensions. Picture a hypercube. At each corner, we place a small hypersphere. In the very center of the hypercube, we place another hypersphere, and we make it just big enough to touch all those little corner spheres. In our 3D world, that central sphere would be tiny, safely tucked away deep inside the cube. But as we increase the dimensions, something strange happens to distance. By the time we get to the 5th dimension, that central sphere we put inside, which is only supposed to touch the asterisk corner spheres, has grown so large it's now poking out through the faces of the hypercube. By the 10th dimension, the central sphere is so enormous it completely swallows the hypercube it's supposed to be inside of. Think about that. Our basic intuitions about inside, outside, and distance completely fail in higher dimensions. It's a space that can be simultaneously emptier, with shrinking sphere volumes, and yet more complex, letting objects connect in ways that seem impossible to us. This isn't just math games. This is the kind of world our bubble universe could be floating in. A world that is emptier, pointier, and more interconnected than ours. A place where our rules of geometry are just a simplified, local version of a much grander and stranger reality. If we ever found a way to peek into the bulk, we would be the square from Flatland, yanked into Spaceland for the first time, confronted with a reality so alien and complex it would redefine the very meaning of space itself. If your brain is starting to hurt trying to picture a fifth dimension, then you're in the right place. Subscribe to this channel, because we are all about exploring these boundary-pushing ideas and redrawing the map of reality. And please, leave a comment below. If a being from the fourth dimension could see and interact with our world, what do you think would be the most profound or terrifying thing they could do? I'm genuinely curious to hear what you all come up with. Can we ever know for sure? This is all a fascinating, mind-bending story. A multiverse of colliding branes, a cosmos of infinite cycles, living in a higher dimension. But is it science? Or is it just a cool story made of math? A theory is only as good as its ability to be tested. So, is there any way we could ever find actual, physical evidence that our universe is a brane in a higher dimensional bulk? Surprisingly, the answer is yes. This theory, as wild as it sounds, makes several real, testable predictions. The first and most direct clues would come from gravity. In many of these models, gravity is the one thing that can travel through the bulk. This could show up in a couple of ways. First, at very small scales, gravity might stop behaving as we expect. Newton's famous inverse square law, which says gravity gets weaker with the square of the distance, works because it's spreading out in 3 dimensions. If there are extra dimensions that open up at very tiny distances, gravity could leak into them faster, causing its force to drop off more rapidly than the inverse square law predicts. There are ultra-sensitive experiments right now trying to measure gravity at sub-millimeter scales, looking for exactly these kinds of changes. So far, Newton's law is holding up, but they keep pushing the limits. A much more dramatic signal would be finding gravitational waves from another dimension. Imagine another brane colliding with our Big Bang. An event like that would send shockwaves not just through our brane, but through the entire bulk. It's also possible that a collision with a smaller object, or even a close pass with another brane universe, could send gravitational ripples through the bulk that would register here. Our detectors, like LIGO, are listening for ripples in our 3D spacetime. While they haven't heard anything like this yet, some theorists think a constant background hum of high-frequency gravitational waves could be a sign of extra-dimensional activity, like hearing the faint, steady roar of a distant cosmic ocean. The second major hunting ground is at the world's most powerful particle accelerator, the Large Hadron Collider, LHC. The logic is pretty straightforward. If you smash particles together with enough energy, you might be able to knock some of the shrapnel off our brane and into the bulk. How would we see that? By looking for missing energy. In any collision, the total energy you start with must equal the total energy you end with. The giant detectors at the LHC are built to be sealed systems, to catch every particle that flies out. If, after a smash-up, scientists add up all the energy and find that some is gone, it would be a smoking gun. It could mean a particle, maybe a graviton, was created and instantly vanished into the bulk, taking its energy with it, forever invisible to us. They are actively looking for this, but so far, all the energy has been accounted for. An even more spectacular find at the LHC would be the creation of tiny, microscopic black holes. In our 3D universe, the energy needed to create a black hole is astronomical, far beyond what the LHC can do. But if there are large extra dimensions, gravity could be much stronger at small distances, drastically lowering the energy needed. If this happened, these micro black holes wouldn't be dangerous. They'd evaporate almost instantly in a flash of particles called Hawking radiation. This would create an explosive, unmistakable signature in the detectors. Seeing it would not only confirm extra dimensions but would let us study quantum gravity in a lab. But again, the searches have come up empty. Finally, we can look for clues in the sky. The cosmic microwave background, CMB, is a baby picture of our universe. If our universe was formed by a collision, it's possible the event left a bruise on our cosmos. Specific patterns or large, cold spots that don't quite fit the standard model. Scientists have mapped the CMB in incredible detail, and while there are some strange anomalies, none can be definitively tied to a brane-world collision. So, for now, in every experiment we can devise, our universe still looks stubbornly three-dimensional. There is no proof. But the fact that we can even ask these questions and design experiments to hunt for the answers shows how far we've come. We are no longer just mapping our world. We are searching for the edges of our reality itself. We started this with a simple idea: a two-dimensional world trying to imagine a third dimension. We saw how its inhabitants, the Flatlanders, would be prisoners of their own perception, totally blind to the bigger reality right next to them. We've explored the very real possibility that we are in the exact same boat. That our entire, seemingly infinite cosmos is nothing more than a delicate bubble, a brane, floating in a higher dimensional space called the bulk. We've seen how this idea, born from the dense mathematics of string theory, offers stunning solutions to some of physics' deepest puzzles, from the weakness of gravity to the origin of the Big Bang itself. It paints a picture of a universe born not from a singular, unknowable event, but from a fiery collision between two parallel realities, just one moment in a potentially endless cycle of cosmic death and rebirth. A cosmos where our Big Bang was not the beginning, but simply our beginning. We've tried to peer into the bizarre, alien geometry of this higher dimensional bulk, a place where our fundamental ideas of shape and space break down. And we've walked through the scientific battlegrounds where this grand theory is being put to the test in the faint whispers of gravitational waves, in the hunt for missing energy, and in the ancient light of the cosmos. For now, the bulk remains hidden. But the idea is out there. It forces us to face the possibility that everything we know, every star, every galaxy, every law of physics is confined to a tiny slice of a much larger, grander, and stranger reality. It suggests that just beyond the reach of our senses, other universes may be floating silently in the dark, each with its own story, each a bubble in an infinite cosmic foam. The next time you look up at the night sky, at the stars and the galaxies all rushing away from each other, just take a moment to wonder. Are you seeing the expansion of a singular universe? Or are you living on the skin of an expanding bubble, a membrane stretching out into a dimension you can never touch, growing inside something that, just maybe, is watching us back? Our universe is a bubble and we're trapped inside. Look out into the night sky. Past the city lights, past the moon, deep into the blackness between the stars. Everything you've ever known, every person who has ever lived, every secret ever whispered and every victory ever shouted, happened right here, on a tiny speck of dust we call Earth. And this speck of dust lives inside a colossal structure we call our universe. It holds every star you can see, every galaxy the Hubble and Webb telescopes have ever shown us, every cosmic event across 13.8 billion years of history. We see its breathtaking scale, its seemingly infinite complexity, and we naturally assume, well, that this is it. This is everything. But what if all of it, everything, is just a single bubble, floating in an endless, unseen cosmic ocean? What if the Big Bang wasn't the beginning of time, but just the moment our bubble started to inflate? What if our entire existence is just a thin film, a membrane, adrift in a higher dimensional reality we can never touch? And the most unsettling question of all: what if we're trapped inside? Today, physicists are seriously exploring this mind-bending theory. It's the idea that our universe isn't all there is, but just one part of a far grander, and much weirder, multi-dimensional reality. We're going to explore the science behind brane theory, the radical notion that our cosmos is a bubble. We'll look at the bizarre physics of extra dimensions, and we'll join the hunt for clues, faint whispers from the dawn of time, and strange signals in our most powerful particle colliders that could reveal the larger reality our universe is expanding in. What we find might just change how you see everything, forever. The universe we know, the problem of our limited view. To even begin to understand how our reality could be a bubble, we first have to get a handle on the bubble itself. For the last century, we've been building a stunningly successful picture of our cosmos. We call it the Standard Model of Cosmology, and it's built on a few key pillars of observation. It all kicked off in the 1920s, when Edwin Hubble discovered something that would forever change our place in the cosmos. He saw that distant galaxies weren't just sitting still. They were all moving away from us. And the farther away a galaxy was, the faster it was speeding off. Now, this wasn't like an explosion with everything flying out from one central point. The visual is more elegant and more profound. Imagine a loaf of raisin bread rising in the oven. Pick any raisin, it doesn't matter which one. From its perspective, all the other raisins are moving away. The raisins themselves aren't moving through the dough. The dough itself, the very fabric of space, is expanding, carrying the raisins along for the ride. That's our universe. It has no center, and every point is stretching away from every other point. This stretching of space-time causes light from distant objects to shift toward the red end of the spectrum, something called redshift. Hubble's discovery that redshift increases with distance was the first real proof that our universe is dynamic and growing. But if it's expanding now, then it must have been smaller, denser, and hotter in the past. If you rewind the cosmic clock, all of space, all the matter and energy in our universe, squeezes down into an infinitesimally small, unimaginably hot point. That's the heart of the Big Bang theory. The idea is that our universe burst into being about 13.8 billion years ago from this singular state and has been expanding and cooling ever since. For decades, this was a powerful but incomplete idea. The ultimate proof landed in 1965 with the accidental discovery of the cosmic microwave background, or CMB. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to get rid of a persistent, faint hiss in their radio antenna. This hiss was the same no matter where they pointed it, day or night. What they'd found wasn't a glitch. It was the echo of creation. The CMB is the afterglow of the Big Bang. It's a baby picture of the universe when it was just 380,000 years old. Back then, the cosmos was a hot, dense soup of protons, electrons, and photons. Light was trapped, constantly bouncing off free electrons. But as the universe expanded and cooled, protons and electrons finally came together to form neutral atoms. In that moment, the universe became transparent. The trapped light was set free, and it has been traveling across the cosmos ever since, cooling and stretching into the faint microwave radiation we detect today. This ancient light is almost perfectly the same temperature everywhere, which tells us the early universe was incredibly smooth. But it also has tiny temperature fluctuations, variations of just 1 part in 100,000. These little ripples, these slightly hotter and colder spots, were the seeds of everything. Over billions of years, gravity pulled more and more matter into the denser spots, forming the stars, galaxies, and massive clusters we see today. The Big Bang model, backed up by the expansion of space and the CMB, is the bedrock of modern cosmology. It tells a coherent story of where we came from. But as our observations have gotten sharper, we've started to notice some deep and troubling cracks in this beautiful picture puzzle, so profound they suggest our entire understanding of reality is incomplete. Cracks in the picture. The mysteries that demand new ideas. The standard Big Bang model is a scientific triumph, but it's not perfect. It describes how the universe evolved from that hot, dense state, but it leaves some of the biggest questions unanswered. It's these loose threads that have forced physicists to think outside the box, or in this case, outside the bubble. The first major puzzle is the asterisk flatness problem. On the largest scales, our universe appears to be geometrically flat. Now, this doesn't mean it's two-dimensional. In cosmology, flat describes the overall geometry of spacetime. According to Einstein's general relativity, mass and energy curve spacetime. The universe could be positively curved, like a sphere, where parallel lines eventually meet. It could be negatively curved, like a saddle, where they diverge. Or it could be perfectly flat, like a sheet of paper, where parallel lines stay parallel forever. Our measurements show our universe is incredibly, ridiculously close to being perfectly flat. And that's a problem. Any tiny deviation from perfect flatness in the early universe would have been magnified enormously over 13.8 billion years. For it to be this flat today, the universe at 1 second old had to be flat to 1 part in a quadrillion. That's like balancing a pencil on its sharpest point and having it stay perfectly upright for billions of years. It feels less like a coincidence and more like some mechanism we don't understand forced it to be flat. The second puzzle is the asterisk horizon problem. When we look at the cosmic microwave background, we see that it has almost the exact same temperature in every direction. The light from one side of the sky is the same temperature as the light from the complete opposite side, to 999% accuracy. That might not sound weird, but remember the universe was only 380,000 years old when that light was emitted. Back then, those two opposite regions of the sky were separated by way more distance than light could have possibly traveled in that time. They were outside each other's causal horizon. There's no way they could have ever interacted, exchanged heat, or settled down to the same temperature. So how did they know to be identical? It's like finding two people on opposite sides of an uncrossable desert who have, by pure chance, written the exact same 1,000-page novel, word for word. The standard model just says, that's how it was. Then there's maybe the biggest crack of all: dark energy. In 1998, astronomers discovered the expansion of the universe isn't slowing down under gravity's pull, it's speeding up. To explain this, they proposed a mysterious force, a kind of anti-gravity, which they called dark energy. It seems to be a property of space itself, and today it makes up nearly 70% of the universe's energy. Our best idea for dark energy is the cosmological constant, which represents the energy of empty space. The problem is, when we use quantum physics to calculate how much energy the vacuum should have, the number is catastrophically wrong. The prediction is about 10 to the power of 120 times larger than what we actually observe. That's a 1 followed by 120 zeros. This has been called the worst theoretical prediction in the history of physics. It's a massive clash between our theory of gravity and our theory of the very small, signaling we're missing something huge. Finally, there's a more recent crisis known as the asterisk Hubble tension. It's a stubborn disagreement over how fast the universe is expanding right now. We have two main ways of measuring this value: the Hubble constant. One method uses early universe data from the cosmic microwave background, which predicts an expansion rate of about 67 kilometers per second per megaparsec. But when we use late universe methods, like observing stars in nearby galaxies, we get a different number, around 73. For years, everyone hoped it was just a measurement error. But as both types of measurements get more precise, the tension has only gotten stronger, suggesting our standard model connecting the early and late universe might be wrong. These problems, flatness, horizons, dark energy, and the Hubble tension, aren't minor details. They are gaping holes in our cosmic story. They are the reason scientists are searching for new physics, for ideas that go beyond the standard model. And one of the most audacious is that our universe is just a membrane. A new dimension, introducing brane theory. To solve these deep puzzles, some physicists think we need to change our most basic assumption: how many dimensions our universe actually has. This idea comes from one of the most ambitious and controversial theories out there: string theory. String theory's main idea is that the fundamental bits of reality aren't tiny dots, but tiny, vibrating one-dimensional strings. Different vibrations of these strings produce all the different particles we see. But for the math to work, it requires something shocking. The universe must have more than the 3 spatial dimensions we know. Most versions need 10 or 11 dimensions in total. So, where are they? The classic answer was that they're compactified, curled up into a microscopic size, so small we'd never notice. Imagine a garden hose. From far away, it looks like a one-dimensional line. But for an ant on its surface, it clearly has a second dimension: the part that goes around. In the same way, at every single point in our space, there could be tiny, curled-up dimensions, hidden from our view. But in the 1990s, a revolution in string theory offered a new, even wilder possibility. The theory didn't just contain 1D strings. It also included higher dimensional objects called branes. And this led to a radical new picture. What if our entire universe is a giant brane? This is the core of brane cosmology. In this model, our universe is a vast, three-dimensional membrane, a 3 brane, floating in a higher dimensional space called the bulk. You, me, and all the matter and forces we know are stuck to this brane. Think of that ant on the garden hose again. It's born on the hose, lives on the hose, and dies on the hose. It can only move along the hose's 2 dimensions. It might feel things from the larger 3D garden, like wind or tremors, but it can never leave the 2D surface. According to brane theory, we're the ants. All the particles of the standard model, the photons, electrons, everything are like open strings, with their ends stuck firmly to our 3 brane. We are fundamentally bound to our membrane, unable to leap off into the higher dimensional bulk. But there's one crucial exception: gravity. In string theory, gravity isn't an open string. It's a closed loop. And a closed loop has no ends to get stuck on the brane. This means that unlike light or matter, the particle that carries gravity, the hypothetical graviton, is free to travel through all the dimensions, both on our brane and into the bulk. This offers a startlingly elegant solution to another huge puzzle in physics. Why is gravity so weak? It's trillions of times weaker than the other forces. A tiny fridge magnet can lift a paperclip, its electromagnetic force easily overpowering the gravitational pull of the entire planet. Brane theory says gravity isn't actually weak. It's just as strong as the other forces, but its strength gets diluted. Because gravitons can leak off our brane and spread out into the vastness of the bulk, we only feel a tiny fraction of gravity's true power. It's like a light bulb in a big, foggy room. Its light quickly fades into the surrounding space. The other forces are like lights shining right on our brane, so we feel their full glare. This idea makes testable predictions. Dark energy, the mysterious force accelerating our expansion, might not be an energy of our vacuum at all. It could be the result of forces between our brane and other branes in the bulk. And most excitingly, this completely rewrites the story of the Big Bang. If our universe is a bubble, then its origin might not have been a singularity, but something even more dramatic. A collision. The Big Bang reimagined, the ekpyrotic and cyclic universe. The standard Big Bang model says our universe began from a singularity, a point of infinite density where the laws of physics break down. Physicists have never been comfortable with singularities. Brane cosmology offers a way out, a scenario that avoids a singularity by reimagining the Big Bang not as a beginning, but as a violent encounter in a higher dimension. This alternative is called the ekpyrotic model, a name from an ancient Greek idea of a cosmic conflagration, or fiery rebirth. Proposed in 2001, it's a speculative but fascinating idea. In this scenario, our universe is one of two parallel three branes floating in a higher dimensional bulk, separated by a tiny gap. For eons, these branes might be cold, empty, and nearly parallel. But a force is slowly pulling them together. As they get closer, tiny quantum fluctuations on their surfaces, microscopic wrinkles, are stretched and amplified. Finally, the branes collide. It's a universe-spanning event where the energy of the collision is converted into a colossal burst of matter and radiation, instantly heating our brane to an incredible temperature. To anyone on our brane, this would look exactly like a Big Bang. It marks the start of the hot, dense, expanding universe we know. The wrinkles on the branes right before the crash would be imprinted onto the new matter, becoming the very same temperature variations we see in the cosmic microwave background. This model elegantly solves the flatness and horizon problems without needing inflation. The branes are assumed to have evolved to be parallel and uniform over a long, slow period before the collision. The crash itself happens almost at the same time everywhere, ensuring the new universe starts out with the same temperature everywhere. The ekpyrotic model can be stretched into an even grander vision. The cyclic universe. After the collision, the branes bounce apart, and our universe starts its long journey of expansion and cooling. Stars and galaxies form. Life emerges. Over trillions of years, dark energy stretches the universe until it's cold, empty, and smooth once more. But the story doesn't end there. The force between the branes eventually overcomes the expansion, and they start moving toward each other again. The cycle repeats. A new collision, a new Big Bang, and a new universe is born from the ashes of the old. Our Big Bang would be just one chapter in an endless cosmic story. It's a beautiful idea. But is it science? Can we ever find proof? The hunt for clues is on, in the largest machines ever built and in the faintest light from the dawn of time. The hunt for evidence. Searching for the bulk. A theory is just a good story until you can test it. The idea of extra dimensions and colliding branes might sound like science fiction, but it makes some real predictions we could actually observe. The search is happening on two very different fronts. In the crazy high energies of particle colliders, and in the ancient light of the cosmic microwave background. Our first hunting ground is the Large Hadron Collider, or LHC. This 27-kilometer ring smashes protons together at nearly the speed of light to recreate the conditions of the early universe. If the brane world idea is right, these collisions could give us a peek into the bulk. One of the most spectacular predictions is the creation of micro black holes. If two particles collide with enough energy in a small enough space, they could get close enough to feel the full, undiluted force of gravity and collapse into a tiny black hole. These would be totally harmless, evaporating almost instantly in a distinct spray of particles. Finding one would be a smoking gun for extra dimensions. Another sign would be missing energy. An energetic collision could literally knock a particle off our brane, sending a graviton flying into the bulk. Our detectors, being stuck on the brane, would never see it. We'd just see an imbalance, less energy coming out of a collision than what went in. So, what have we found? After years of running and sifting through quadrillions of collisions, the LHC has found nothing. No micro black holes, no missing energy. This doesn't kill the theory, but it does constrain it. It means if these extra dimensions exist, the energy needed to access them is higher than what the LHC can reach right now. Our second hunting ground is the sky itself, specifically the cosmic microwave background. If our universe was born from a brane collision, it might have left a specific pattern in the CMB's temperature map. For a while, there was an exciting candidate, the *CMB cold spot. This is a large patch of the sky that is weirdly cold. It was tantalizing to think this could be a bruise from another bubble universe bumping into ours. However, a more down-to-earth explanation has emerged. The cold spot seems to line up with a massive supervoid, a colossal, unusually empty region of space between us and the CMB. Light from the CMB loses energy passing through a void, making it appear colder. While this supervoid might not explain the asterisk entire temperature drop, most cosmologists now think the cold spot is probably just a rare statistical fluke, not proof of a multiverse. A more promising test is the search for primordial asterisk gravitational waves. Both inflation and ekpyrotic models predict these ripples in spacetime, but they predict different kinds. Inflation generally predicts a sea of gravitational waves that should be detectable. Finding them would be a huge win for inflation. Ekpyrotic models, on the other hand, predict a much weaker signal that would be virtually undetectable. This creates a clear test. If future sensitive detectors find primordial gravitational waves, it's a major blow to cyclic models. But if they find nothing, decade after decade, the absence of a signal would itself become powerful evidence for a bouncing, cyclic cosmology. The edge paradox. If we're in a bubble, where's the edge? The idea of a bubble universe immediately makes you ask a simple question. Can we get to the edge? And what happens if we do? This is a modern version of an ancient puzzle. The philosopher Lucretius imagined throwing a spear at the edge of the universe. If it keeps going, there is no edge. If it stops, something outside must have stopped it, which means that is the new edge. It seems logically impossible for the universe to have a boundary. Modern cosmology solves this paradox with a geometric twist. The universe can be finite without having an edge. Think about the surface of the Earth. It's a finite, two-dimensional surface. You can travel about 40,000 kilometers and you'll end up right back where you started. The Earth's surface is finite, but it has no edge to fall off of. It's a finite, unbounded space. Our three-dimensional universe could be the same way, just in a higher dimension. It could be a 3-sphere, or a 3D donut shape. If you flew a spaceship in a straight line, you wouldn't hit a wall. You'd just eventually arrive back where you started, from the opposite direction. Brane theory offers a profound twist on this. Our 3D universe, our brane, is also edgeless in its own dimensions. You can't find a wall on the brane. But the bubble does have a boundary. The transition into the higher dimensions of the bulk. The catch? We can't get there. All of our matter, the very stuff we're made of, is stuck to the brane. Trying to leave our 3D brane and enter the 4D bulk would be like a character in a movie trying to climb out of the screen and into the theater. It's a fundamentally impossible move. So, the answer to where is the edge is twofold. In our dimensions, there is no edge. But in the context of a higher dimensional reality, the edge is all around us, in a direction we can't point to or travel in. We are confined to our bubble, not by walls, but by the very laws of physics that make us. The fate of our bubble, expansion, contraction, and the future. For the last 25 years, the fate of our universe seemed pretty much settled. The discovery of dark energy showed our expansion is accelerating, pointing to a lonely and cold future. In this Big Freeze scenario, the expansion would go on forever. Galaxies would fly apart so fast their light could no longer reach us. The sky would go dark. Stars would burn out. The universe would become a graveyard of black holes and dead stars, which would themselves evaporate over trillions of years, leaving a cold, dilute soup of particles in an endless, empty darkness. This was the consensus, assuming dark energy was an unchanging, cosmological constant. But what if dark energy isn't constant? What if it changes over time? This idea is called quintessence. For years, it was just a theory. But now, startling new data is giving us the first tantalizing hints that dark energy might be weakening. Massive projects like the Dark Energy Survey, DAY, and the Dark Energy Spectroscopic Instrument, DAISY, have made the largest 3D maps of the universe ever. Their recent results from 2025 and 2026 suggest something remarkable. The data hints that dark energy may be evolving. While it's not yet statistically conclusive, the evidence suggests the repulsive force of dark energy may be fading over cosmic time. This changes everything. If dark energy is weakening, the cosmic tug-of-war between its outward push and gravity's inward pull could shift. If gravity eventually wins, the expansion could halt and then reverse. This would lead to a completely different fate. The Big Crunch, our universe would begin to contract. Galaxies would start rushing towards us. The sky would get brighter and bluer. The universe would grow hotter and denser, collapsing back into a single, fiery point, a mirror image of the Big Bang. Based on new models incorporating this potential for evolving dark energy, some physicists calculate this big crunch could happen in roughly 20 billion years. And this is where it all comes full circle. A big crunch is exactly what the cyclic universe model needs to work. The collapse of our universe would be the moment our brane rushes back to collide with its partner, triggering a new Big Bang. The data hinting at a big crunch is the first potential piece of observational evidence that gives new life to these cyclic theories. What was once pure speculation now has a faint, but real, connection to data. The future of our bubble is still unwritten. We started with the familiar picture of a single, vast universe. We saw how puzzles in that picture, the flatness, the uniform temperature, the crazy value of dark energy, the Hubble tension, forced us to imagine a more radical reality. We explored the mind-bending idea that our entire cosmos is just a three-dimensional brane, a bubble in a higher dimensional bulk. We saw this idea rewrites our origin story, replacing the Big Bang's singularity with the collision of two universe branes. We followed the hunt for evidence, from the LHC to the CMB, a search that's still ongoing. We grappled with the edge paradox, only to find we're trapped on our brane, unable to touch the larger reality around us. And finally, we saw how the universe's presumed fate, a cold, slow death, is now being challenged by our latest observations. New data suggests dark energy may be fading, opening the door for a future big crunch, a fiery end that could also be the beginning of an eternal, cyclic universe. These are the absolute frontiers of science. Brane cosmology and cyclic models are not proven fact. They are speculative frameworks designed to solve the deepest mysteries we face. The idea that we're trapped inside a bubble might sound diminishing. It can make our entire existence seem like a tiny footnote. But there's another way to look at it. It means that reality is infinitely grander and more complex than we ever imagined. It means the laws of nature might be written not in 3 dimensions, but in 10 or 11. It means the beginning of our time may not have been the beginning of all time. The quest to understand our place in the cosmos is the greatest adventure we can undertake. For our species, on one small planet, in one bubble universe, to piece together this story and actively search for what lies beyond. That's not diminishing. It's magnificent. The universe is whispering its secrets. And we are, finally, learning how to listen. If you enjoy exploring the biggest questions in the universe, consider subscribing to join our community. We have so much more of the cosmos to investigate together. A 4D being is watching our universe inflate. From where I'm standing, it starts as the smallest of things. A flicker. A tiny, perfect sphere of light that just appears. To my senses, it's just a new bubble in the substrate of reality, no different from the countless others that shimmer in and out of existence. But this one feels different. I can see all of it at once, its past, its present, its future, laid out before me like a single, complete thought. And as it begins to swell, I see patterns forming on its surface. Intricate, fractal webs of light and shadow. The inhabitants who will one day live deep inside that bubble, on one of those delicate patterns, will call them galaxies. To them, their beginning is a fiery, chaotic explosion. To me, it's a silent, breathtaking bloom. What if the Big Bang, the most cataclysmic event we can imagine, was actually a quiet and graceful unfolding when seen from another perspective? It sounds like something out of a novel, but the question is rooted in one of the most mind-bending thought experiments in all of physics. The concept of higher dimensions. We are creatures of 3 spatial dimensions. We can move forward and backward, left and right, up and down. That's our world. But what if our entire, vast, 3-dimensional cosmos is just a thin membrane floating in a larger, 4-dimensional space? A space with an extra direction completely invisible and inaccessible to us. If a space like that exists, and if a being could live inside it, how would they see our universe? What would they have witnessed 13.8 billion years ago? The story they could tell would be radically different from our own. Today, we're going on a conceptual journey. We're going to climb the ladder of dimensions, rung by rung, using the tools of analogy and scientific theory. First, we'll ground ourselves in the universe we know, the one we see from the inside out, a universe of expanding space and galaxies flying apart. Then, we'll take a leap of imagination, guided by physics, to see what that exact same expansion might look like from the outside. Is our universe a growing crystal? An inflating lung? Or something else entirely? This journey might just challenge your very definition of what it means to exist. Our familiar universe. The view from inside. Before we can step outside, we have to understand the room we're in. Our modern picture of the cosmos really began about a century ago, with a couple of startling discoveries. When astronomers like Edwin Hubble pointed their telescopes at faint, fuzzy patches of light they called nebulae, they found, first, that these weren't just gas clouds in our own galaxy. They were entire, separate galaxies, islands of stars just like our Milky Way, millions or billions of light years away. But the second discovery changed everything. When they analyzed the light from these distant galaxies, they found it was stretched. The light was shifted towards the red end of the spectrum. This cosmological redshift was a cosmic-scale Doppler effect, and it meant that almost every galaxy, in every direction, is moving away from us. And the farther away it is, the faster it seems to be going. The immediate picture this paints is of a colossal explosion, all matter flying outwards from a single point in space, like shrapnel from a bomb. But that picture, while intuitive, is fundamentally wrong. And understanding why is the key to everything. The galaxies aren't flying through space. Space itself is expanding. It's a subtle difference, but it's a crucial one. To get it, we need our first and most famous analogy, the inflating balloon. Imagine you're a two-dimensional being living on the surface of a balloon. Your entire universe is that 2D rubber sheet. Now, a being from the third dimension starts inflating it. What do you see? If you draw dots on the balloon to represent galaxies, you'll notice that as it inflates, every dot moves away from every other dot. There is no center of the expansion asterisk on the surface. Pick any dot you like, and it will look like the center. This is exactly what we observe. Our galaxy isn't special. An observer anywhere else would see the same thing. The dots aren't really moving across the rubber, either. They're being carried along by the stretching of the rubber itself. The space between them is what's growing. A light wave traveling from one dot to another would also get stretched out, its wavelength getting longer. That's cosmological redshift, not from motion through space, but from space itself expanding. Another great analogy is a loaf of raisin bread rising in the oven. The raisins are galaxies, and the dough is space. As the dough expands, all the raisins move apart, and the more distant ones move away faster because there's more expanding dough between them. We aren't flying through some pre-existing void. We're just passengers on a dynamic, growing space-time. This is the universe from our perspective. For decades, we thought this expansion was slowing down, thanks to gravity. But then, in 1998, we found out the expansion is actually accelerating. To explain this, cosmologists proposed a mysterious force called dark energy, woven into the fabric of space itself, that acts like a constant push. This picture got even weirder in the mid-2020s. Some new data has started to hint that dark energy might not be so constant after all, with some studies suggesting the acceleration could even be slowing down now after a long period of speeding up. Other researchers propose we might not even need dark energy, and that the acceleration is just a natural feature of spacetime's geometry. But whether it's constant, evolving, or an illusion, the core observation is the same. Space is stretching. It has no edge and no center we can point to. From here, it looks infinite. But that balloon analogy holds a secret. The 2D surface is finite and has no center asterisk on the surface. But in the third dimension, a center clearly exists. The point inside the balloon. The 2D expansion is only truly understood from a 3D perspective. And that brings us to the ultimate question. Could our 3D universe be doing the same thing? Is there a fourth spatial dimension from which the true shape of our cosmos is obvious? To answer that, we first have to learn how to see in 4 dimensions. Climbing the ladder of perception, understanding dimensions. The idea of a fourth spatial dimension feels impossible. Our brains are wired for 3. But we can build an understanding through analogy, by taking one step down the dimensional ladder. For this, we can thank a brilliant little book written in 1884 by Edwin Abbott, Flatland. A romance of many dimensions. Imagine a world on a completely flat, 2D plane. The inhabitants, Flatlanders, are geometric shapes. Our hero, a square, can move left and right, forward and backward, but has zero concept of up or down. When he looks at his fellow citizens, he doesn't see their full shape, just a line segment the edge facing him. One day, a visitor arrives. A 3-dimensional sphere. How does the sphere appear to a square? It doesn't arrive all at once. It passes through the plane of Flatland. First, the very bottom of the sphere touches the plane. To a square, a single point materializes out of thin air. As the sphere descends, its cross-section in the 2D plane becomes a small circle. The point has magically grown. As the sphere passes its equator through the plane, the circle grows to its maximum size. Then, it begins to shrink, contracting back to a single point before vanishing as suddenly as it appeared. To the Flatlanders, this is magic. A circle that can change its size at will and pop in and out of existence defies all known physics. A square is terrified. He can't comprehend the single, unified 3D object whose passage is causing this bizarre show. But from our privileged 3D viewpoint, it's perfectly simple. We see the sphere, we see the plane, and we see the straightforward motion. The mystery is just a matter of perspective. We can see inside their locked rooms because we're looking down from above. We see their entire world laid out before us. Now for the leap of imagination. What if we are the Flatlanders? What if our entire three-dimensional existence is just a slice, a cross-section, of a four-dimensional reality, a hyperspace? If a 4D hyper-object passed through our space, it might appear just as magically. A small sphere could materialize from nowhere, expand or warp in ways that seem to violate physics, then shrink and vanish. We'd be like a square, bewildered by a series of disconnected 3D events, while a 4D being would see a single, unchanging 4D object just moving along its path. Thinking this way is a workout for the brain. We can't picture a tesseract, a 4D hypercube, but we can describe it with math. Its shadow in our world is a mesmerizing object, a cube within a cube. This isn't just a game. The Flatland analogy teaches us that a higher dimensional observer sees the whole of a lower dimension at once. And with that tool, we're finally ready to step outside our universe and watch it be born. Before we take that final leap to witness the birth of our cosmos from this new perspective, it's a good moment to pause. If you're enjoying this journey into the mind-bending nature of reality, please take a moment to subscribe and click the notification bell. We're about to view the Big Bang as no human has ever seen it, and you won't want to miss what comes next. The 4D being's grandstand view. The cosmic inflation. Armed with our dimensional analogy, let's become that hypothetical 4D being. We are outside the universe, in a 4D bulk. Our 3D universe is now an object in our space. Let's imagine it as the 3D surface of an expanding 4D hypersphere. This is the direct upgrade from the balloon analogy. A Flatlander's 2D universe is the surface of a 3D sphere. Our 3D universe is the surface of a 4D hypersphere. This model gives us a universe that is finite yet has no boundary. You could travel in a straight line and eventually end up right back where you started. Now, let's rewind time. All the way back. What does our 4D being see? It doesn't see an infinitely dense point asterisk in space. That's part of our inside view. Instead, the 4D being sees the birth of the hypersphere itself. It begins as a tiny point asterisk in the 4D bulk. Then, this point blossoms. It doesn't explode, it inflates. This is cosmic inflation. In the first flicker of a second, a timeframe theorists estimate to be around 10 to the minus 36 seconds, the universe undergoes a period of exponential, faster than light expansion. From the 4D being's perspective, this is a breathtaking show. A point like hypersphere swells at an unbelievable rate. It's not growing into anything. Its own surface is the creation of space. But the 4D being sees more than just a swelling bubble. They can see its texture. At the very beginning, the surface of this hypersphere wasn't perfectly smooth. It was a roiling froth of quantum fluctuations, tiny variations in energy and density. During hyperfast inflation, these microscopic, quantum-level wrinkles are stretched to astronomical size. The 4D being watches as minuscule fluctuations become vast ripples across the 3D surface of the hypersphere. These ripples are the seeds of all future structure areas that are infinitesimally denser than average. As the hypersphere continues to expand and cool, a beautiful process unfolds on its 3D surface. Gravity takes hold. Those denser regions, the stretched-out quantum wrinkles, start pulling in more matter. Over hundreds of millions of years, they become the anchor points for a vast, intricate network we now call the cosmic web. And where these filaments of gas and dark matter intersect, the 4D being sees the surface begin to glow as the first stars ignite and galaxies are born. From our perspective, we see galaxies moving apart. From the 4D being's perspective, they see a static pattern of glowing dust, fixed to the surface of a bubble that is being inflated. Now, let's introduce one of the most mind-bending ideas of all: time. For us, time flows like a river. But for a being that perceives 4 spatial dimensions, our dimension of time might just be another direction. This is a fascinating interpretation of space-time called the block universe, or eternalism. In this view, where past, present, and future all exist at once, our entire cosmic history forms a single, static object. A 4D being wouldn't see our universe happen. They would simply see it, complete and whole. Our sense of time passing is just our consciousness moving through successive slices of this static block. So, the 4D being looks upon our cosmic history not as a movie, but as a sculpture. They see the cone of our timeline, starting at the point of the Big Bang and widening out. They can trace the path of every particle, the formation of Earth, and the entirety of human history, all as different locations on one timeless object. What about today, with the accelerating expansion? Observing this block universe, the 4D being would see the sculpture of our universe, which was curving inward for billions of years, begin to flare outward again. They would see the galactic superclusters on the surface being pulled further and further apart. They might even see its ultimate fate. If the acceleration continues, they see a future where the surface stretches so much that all galaxies are pulled beyond the horizon, leaving behind a cold, dark, and lonely void. Or, if those new theories about acceleration slowing down are correct, they might see the expansion halt in reverse, with the hypersphere shrinking back to a single point in a big crunch. This outside perspective is majestic and complete. It resolves the paradox of a beginning without a center. To the 4D being, our universe is a beautiful, shimmering bubble of reality. Reconnecting to our reality, science and speculation. This has been a wild journey of the imagination. But we have to land and ask, is any of this real? Let's start with the hard science. Einstein's general theory of relativity is our best description of gravity and the universe. Crucially, it describes the asterisk intrinsic geometry of spacetime. This means it doesn't need our universe to be embedded in a higher dimension to be curved. We can measure the curvature of our universe from right here inside it. So far, our measurements suggest the universe is very, very close to being geometrically flat. But there's still room for a slight, large-scale curvature like that of a giant hypersphere. So, general relativity works perfectly fine on its own. However, other, more speculative theories depend on extra dimensions. The most famous is string theory, and its modern version, M-theory. In these models, the fundamental bits of reality are tiny, vibrating strings of energy. For the math to work, it requires not 4, but 10 or 11 spacetime dimensions. So where are they? One idea is that they're curled up incredibly small, forever hidden from us. But another fascinating idea from M-theory is the brane world scenario. In this model, our entire 3D universe is a membrane, or brane, floating in a higher dimensional bulk. The particles and forces that make up our world are stuck to this brane. We can't leave it, and light can't leave it, which is why we can't see into the bulk. There might be one exception: gravity. In some of these models, gravity isn't confined to our brane. This opens the tantalizing possibility that we could detect extra dimensions indirectly, perhaps by sensing the gravitational pull of another brane floating nearby. Physicists at the Large Hadron Collider have searched for signs of extra dimensions, like energy from particle collisions, leaking away into the bulk. So far, these searches have come up empty, but the hunt is very much still on. We are still deep in the realm of theory. The 4D being remains a beautiful metaphor. We have no direct proof of a 4D bulk or that our cosmos is a bubble. The recent detection of a background hum of gravitational waves seems to be well explained by merging supermassive black holes, though some hope it might hold faint echoes of the early universe. A definitive signal from another dimension remains elusive. We began our journey with an impossible view. A being for whom our universe's birth was a silent, graceful bloom. We stepped down into the 2D world of Flatland to understand the limits of perception, then used that analogy to climb back up and witness our own cosmic history from the outside. We saw how expanding space, receding galaxies, and even the flow of time could look completely different from that vantage point. We've returned to our 3D home, grounded again by experiment and observation. The 4D being and their hyperspatial realm remain, for now, a product of mathematical possibility and a powerful thought experiment. But the value of this idea isn't about whether it's literally true. It's about the expansion of our own minds. Trying to imagine this impossible view forces us to confront the idea that reality may be vastly larger and stranger than our senses let on. It reminds us that our understanding of the universe is a snapshot, a single cross-section of a much grander object. The Flatlander could never truly see the sphere, but by grappling with its mystery, he was open to the possibility of a third dimension. In the same way, we may never step outside our universe to see its true shape. But by daring to ask, what if? By striving to imagine the view from a higher place, we take part in the deepest tradition of human curiosity. The quest to understand is our way of reaching. From here, we see stars and galaxies in a dark sky. From a higher perspective, perhaps there is a shimmering, growing bubble of reality. And from a still higher one? The mystery only deepens. The adventure is in the seeing, but the true grandeur is in the seeking. Black holes are secretly doorways to other realities. What if the most destructive force in the universe is also a gateway? We've always seen black holes as the end of the line, a cosmic dead end where matter, space, and even time itself come to a screeching halt. They are the universe's ultimate monsters, swallowing stars for breakfast and letting nothing, not even light, escape their grasp. We've been taught to see them as final. But what if that entire perception is wrong? What if they're not an end, but a beginning? What if, staring into that inescapable void, we're actually looking at a doorway to another reality? Today, we're going on a journey to the very edge of known physics, to a place where science fiction and credible theories start to blur. We're going to explore the speculative, yet mathematically plausible, idea that black holes aren't cosmic prisons, but cosmic portals. We'll see how these gravitational behemoths might be twisting the fabric of reality to connect our universe with others we can't yet see. This isn't a story about what we know for sure, but a trip into what could be. A journey that challenges our deepest assumptions about the cosmos. So, take a deep breath. We're about to fall in. The cosmic monsters we know. Before we can reinvent the black hole, we have to understand the monster we've come to know. Our modern understanding starts with a name you definitely know: Albert Einstein. In 1915, his theory of general relativity completely changed how we see the universe. He showed us that space and time aren't a static backdrop, but a single, unified fabric, space-time. And this fabric isn't rigid, It can be bent, stretched, and warped. What does the warping mass? Think of it like this. Imagine a stretched out rubber sheet. That's empty spacetime. Now, put a bowling ball in the middle. The sheet dips down. That dip is gravity. A marble rolling by gets drawn into the curve. That's how planets orbit stars. The Earth is just following the curve in spacetime that the Sun's mass creates. So, what happens if you take a huge amount of mass and squeeze it into a tiny space? The warp in spacetime becomes extreme. It's not a gentle curve anymore, it's a bottomless pit. That's a black hole. It's a spot where gravity is so strong that the speed you need to get away, the escape velocity, is faster than the speed of light. And since nothing can travel faster than light, anything that crosses the black hole's boundary can never leave. That boundary is called the event horizon. It's not a surface you could touch. It's the point of no return. Imagine you're paddling a canoe on a river flowing toward a giant waterfall. At some point, the current gets so strong that no matter how hard you paddle, you're going over. The event horizon is that point for spacetime. Cross it, and your future has only one destination: the center. And at the center? A concept that has baffled physicists for a century: the singularity. According to general relativity, the singularity is a point of infinite density, where all the black hole's mass is crushed into zero volume. Here, our laws of physics break down. They give answers that make no sense, like dividing by zero. It's where our science just stops. For anything falling in, the journey is famously gruesome. The gravity would stretch you apart in a process called spaghettification. The pull on your feet would be so much stronger than on your head that you'd be elongated into a thin strand of atoms. It is, by all accounts, the most violent end imaginable. This picture, painted by Einstein's theories, is one of pure destruction. A one-way ticket to nowhere. For decades, this was the story. But a huge question remained, a puzzle known as the black hole information paradox. A basic law of physics says that information can never truly be destroyed. You can burn a book, but the information about it still exists in the ash, smoke, and heat. Black holes seem to break this rule. They swallow information, and then, as Stephen Hawking discovered, they slowly evaporate over trillions of years. But the Hawking radiation they emit seems random, holding no trace of what fell in. So, where does the information go? Does it just vanish? This paradox was the first big crack in the terrifying facade of the black hole. It hinted that our story was missing a chapter. To solve it, physicists had to start thinking outside the box, or in this case, outside our entire universe. While the idea of information being transported to another universe is one hypothesis, other potential solutions involve concepts like the holographic principle or the idea that information is encoded on the black hole's event horizon. A universe of bubbles. To imagine a black hole as a doorway, we first need a place for it to lead. For that, we have to consider an idea from theoretical physics that sounds like pure sci-fi: extra dimensions. We experience life in 3 dimensions of space: length, width, height, and one of time. But what if that's just a slice of the full picture? This is the core idea behind brane cosmology, a concept from string theory. The word brane is short for membrane. In these theories, our entire universe is a vast, 3D brane, floating in a much larger, higher dimensional space called the bulk. It might sound like a fun but untestable fantasy. But there's a fascinating twist. According to some of these theories, most of the forces of nature are stuck to our brane. But there's one force that might be different: gravity. Models like the Randall-Sundrum models propose that gravity isn't confined to our brane. It can leak into the bulk and travel across the extra dimensions. This offers a surprisingly neat explanation for a big mystery: Why is gravity so much weaker than other forces? A tiny fridge magnet can beat the gravitational pull of the entire planet Earth. Brane theory suggests this is because we only feel a fraction of gravity's true strength. The rest has leaked away. This is a huge shift in thinking. Suddenly, gravity is our one possible connection to this hidden, larger reality. Experiments at the Large Hadron Collider, LHC, have been looking for evidence of these extra dimensions, like energy leaking out of a particle collision. So far, no definitive proof has been found, but the hunt is still on. So we have this speculative picture. Our universe as a bubble, floating in a higher dimensional space, with gravity as a potential bridge. And if gravity can access these other dimensions, what about an object that is pure, concentrated gravity? What happens to a black hole? The answer is that it could become something far stranger than we ever imagined. Reinventing the black hole. Our image of a black hole has always been simple, a sphere. But the moment you add more spatial dimensions to the equations of relativity, that simplicity shatters. In a universe with 5 or more dimensions, black holes can get weird. The math shows that instead of just a sphere, a black hole could form a black ring, a donut of pure, crushing gravity. There are also theoretical black strings that could stretch through the higher dimensions. It's a whole zoo of gravitational oddities. This happens because, with more dimensions, there are more ways for an object to spin, twisting spacetime in complex ways that are impossible in our world. This isn't just a mathematical curiosity. It gives us a potential smoking gun. Telescopes like the Event Horizon Telescope, EHT, have given us our first direct images of the supermassive black holes at the center of the M87 galaxy and our own Milky Way. These images show a dark shadow surrounded by a bright, glowing ring, and the size and shape are perfectly consistent with the spherical black holes predicted by Einstein's standard theory of general relativity. But if astronomers ever spotted a black hole shadow that was definitively not circular, it would be revolutionary. It would be powerful evidence that extra dimensions are real and that the monster we thought we knew is actually a messenger from a hidden reality. This realization that black holes might be fundamentally different in higher dimensions is the key. Because if a black hole isn't just a one-way trip to a single point, but a complex, higher dimensional object, then where does it lead? The cosmic tunnel. The idea of a tunnel through space-time is almost as old as general relativity. In 1935, Albert Einstein and his colleague Nathan Rosen explored the math of black holes and found a radical possibility: a connection between two different points in space-time. This Einstein-Rosen bridge was the birth of the wormhole. They imagined a black hole's singularity not as an end, but as an entrance to a bridge connecting to a white hole that spews matter out somewhere else. There was a huge problem, though. These bridges are catastrophically unstable. The tunnel would collapse so fast that not even light could make it through. To keep it open, you'd need to prop it up with something called exotic matter, a hypothetical substance that has negative energy or weighs less than nothing. No one has ever found stable exotic matter, and many physicists think it might be impossible. For decades, that seemed to be the end for wormholes. But what if the secret ingredient isn't exotic matter, but extra dimensions? This is where our ideas come together. Some theories propose that the complex geometry of higher dimensional spacetime could stabilize a wormhole on its own. Imagine our universe as one brane, and another parallel universe as a nearby brane. A black string could act as a physical tunnel piercing through both. From our side, we just see a black hole. But passing through the event horizon might not lead to a crushing singularity, but a journey along the string to emerge from another black hole in the other universe. The black hole would be the mouth of the wormhole. This is highly speculative, but it's a speculation built on Einstein's equations. It suggests that doorways between worlds might be a natural consequence of gravity in a multidimensional universe. In this view, black holes aren't just a feature of the universe. They could be the universe's transportation system. A new twist in spacetime. There's another, even more speculative layer to this story. It suggests spacetime doesn't just bend, it can also twist. This hypothetical property is known as spacetime torsion. It's not part of standard general relativity, but it appears in some attempts to unite gravity with quantum mechanics. Imagine twisting a point on a rubber sheet, creating a little swirl. That's torsion. Highly theoretical work has explored what would happen if our universe had this property. The idea is that where spacetime is most stressed inside a black hole, it might not just curve to infinity, but twist itself into a torsion knot. What if the singularity isn't a point of infinite density at all? What if it's a place where spacetime is so intensely twisted that it tears a hole into a different dimension? In this picture, black holes are like cosmic screws, twisting one dimension into another. This twisting force could be what holds a wormhole open, providing a natural alternative to the need for exotic matter. It must be stressed that this is an idea from the fringes of physics. It's a fascinating concept that complements the wormhole theory, but it's not a mainstream view and remains unproven. It paints a picture of a cosmos where the destructive singularity is replaced by a dynamic, geometric engine, but it's a picture that is, for now, pure theory. Hunting for the doorways. This grand vision would be pure philosophy if there weren't some way to even begin to test it. We can't go to a black hole and jump in. But we might be able to create one, a microscopic one, at the Large Hadron Collider, LHC. The LHC smashes particles together at nearly the speed of light to recreate the conditions of the early universe. If there are extra dimensions, they could dramatically lower the energy needed to trigger gravitational collapse, possibly creating a microscopic black hole for a fraction of a second. Such a black hole wouldn't swallow the Earth. It would evaporate almost instantly in a shower of particles. And that shower is the clue. A simple, 4D black hole would radiate particles out evenly. But a higher dimensional black hole, like a spinning black ring, might decay asymmetrically, spraying particles in a specific pattern. Scientists could search for that unique signature in the collision data. Another angle is gravitational wave astronomy. Instruments like LIGO can hear ripples in spacetime from colliding black holes. For now, the signals we've detected perfectly match Einstein's predictions for standard black holes. But as our detectors get more sensitive, maybe we could hear subtle clues, a ring-down vibration that hints at a higher dimensional shape. To be absolutely clear, no such evidence has been found. The LHC has not yet created a micro-black hole, and our gravitational wave detectors haven't heard whispers from another dimension. These theories remain on the cutting edge, beautiful in their math but unconfirmed by observation. The hunt is on, and it's one of the most exciting quests in all of science. If the idea of finding a doorway to another universe inside a particle accelerator blows your mind, then you'll love the other cosmic mysteries we explore. These questions are why we do what we do. To join us on these journeys, hit that subscribe button and ring the bell so you don't miss our next voyage into the unknown. Building the cosmic architecture. So let's step back and assemble these pieces into a single, breathtaking vision. Let's build the speculative, but coherent, architecture of a multiverse connected by black holes. The foundation is a vast, multidimensional reality, the bulk. Floating in this bulk are countless universes, including our own, like bubbles in a cosmic foam. They are mostly separate, but not entirely alone. The points of connection, the rivets holding this multiverse together, are what we see as black holes. From our vantage point, we see them as regions of such intense gravity that nothing escapes. We see endings. But from a higher dimensional view, they could be the mouths of tunnels, wormholes stabilized not by impossible matter, but by the very geometry of a higher reality, perhaps reinforced by a fundamental twist in spacetime itself. The information that falls into a black hole isn't destroyed, it's just transported. The information paradox that stumped physicists could be resolved in the most elegant way imaginable. The information just leaves our universe and enters another. This is a profound vision. It replaces a universe of isolated endings with a cosmos of infinite beginnings. It transforms the cosmic monster into a cosmic pillar. But is this beautiful, speculative architecture real? From endings to beginnings, we started with the familiar image of a black hole. A cosmic prison, a one-way street to oblivion. We saw it as a place where the laws of physics give up. But by daring to ask, what if we've traveled through layers of speculative science to a radically different place? We expanded our reality, imagining our universe as just one part of a multidimensional tapestry. We reinvented the black hole, seeing it morph from a simple sphere into a zoo of complex, higher dimensional shapes. We found, within its mathematics, the asterisk potential for a stable bridge held open by the very geometry of these hidden dimensions. This story of brines, black strings, and torsion is not established fact. It is a narrative told with the language of advanced mathematics, a what if story that physicists are exploring at the absolute frontier of knowledge. It is a potential solution to some of the deepest puzzles in science, but it's waiting for the crucial test of observation. It is a possibility. And what a possibility it is! It suggests that the universe may have built its own doorways, and that the most enigmatic objects within it are not signs of an ending, but invitations to a larger reality. So the next time you look up at the night sky, and you think of those dark, silent voids, don't just see them as graves for stars. See them as a question mark, a potential, a whisper from a reality that might be just next door, waiting to be discovered. The universe may have built doorways. Now, we just have to figure out if we can ever learn to open them. The universe isn't a simulation, it's a cell. We've all heard the theory. It's a ghost in the machine of modern thought. The idea that our reality, everything we see and feel, is just a sophisticated computer program. That our lives are lines of code, our choices just branches in a decision tree, and our universe a hard drive of unimaginable size. It's an idea born from our digital world, a reflection of our own technology cast upon the cosmos. We hunt for glitches in the matrix, for pixels in the sky, desperate for proof that we're living inside some grand machine. But what if that's a failure of imagination? What if the code we're looking for isn't binary, but biological? What if the operating system of reality isn't built on processors, but on metabolism and mitosis? This proposition is far stranger, more ancient, and deeply personal. What if the universe isn't a machine at all? What if it's alive? What if the entire cosmos, in all its breathtaking immensity, is a single, living cell? The simulation hypothesis. Our digital ghost. Before we get to the truly weird, organic stuff, let's give a nod to the idea that has captured the modern imagination so completely. The simulation hypothesis. Popularized by philosopher Nick Bostrom, it's become the go-to thought experiment of our time. And for good reason, the arguments are seductively logical. First, there's the simple argument of probability. If any civilization, ever, reaches a point where it can run ancestor simulations, think hyper-realistic video games of the past, it will likely run billions of them. If that's true, simple statistics suggest it's overwhelmingly more likely that we are in one of the countless simulations than in the one, original, base reality. Second, the universe itself seems to be written in math. From Einstein's elegant equations to the bizarre rules of quantum mechanics, our reality can be described with stunning precision by numbers. This has led many to wonder if the universe isn't just described by math, but if it is math. Some physicists have even pointed to parallels between error correction in quantum computing and certain equations in string theory, seeing it as a hint that the system is designed to be bug-free. For years, these arguments felt like an unbreakable loop of logic. But recently, a new challenger entered the ring. In 2025, a team of physicists argued that the universe actually cannot be a simulation. Using Gödel's incompleteness theorem, they demonstrated that a complete model of reality requires a level of non-algorithmic understanding that a computer, by its very definition, cannot possess. In other words, the universe is unsimulatable because it's more than just a set of rules and instructions. It transcends computation. This gets to the heart of the simulation hypothesis's main limitation. It's a form of technological narcissism. We are toolmakers, and our greatest tool is the computer. So, we look at the stars and see a server farm. A century ago, we might have seen a grand clockwork mechanism. We project our own peak technology onto the cosmos. We assume that if there is a creator, it must be a programmer. But what if the creator isn't a programmer? What if it's a parent? And what if the process isn't computation, but procreation? To explore that, we have to abandon the cold logic of silicon and dive into the messy, beautiful world of biology. The pivot. Beyond the binary. So, let's take that leap. Let's unplug from the digital and connect to the organic. Let's explore a concept that runs not on code, but on chemistry, not on processing power, but on the power of life itself. The idea that our universe is a biological cell. At first, this sounds like pure fantasy, a metaphor stretched way too far. But as we'll see, this perspective is supported by some startling parallels between the largest structures in the cosmos and the smallest structures of life. It's an idea that reframes our biggest scientific puzzles, turning them from problems of physics into questions of biology. Now, to be clear, you won't find this in a standard physics textbook. This isn't a mainstream scientific theory. But it is a powerful speculative idea that forces us to ask a different set of questions. Instead of, who wrote the code? We can ask, what is the metabolism? Instead of, what's the purpose of the simulation? We can ask, what's the function of the cell? The universe as a living thing is an ancient idea, from the Greek concept of the anima mundi, or world soul. But today, we can take it beyond philosophy. We can compare, measure, and look at the data to see if this old intuition holds up. We can look at the architecture of the cosmos and the architecture of a cell and ask an audacious question. Are we seeing the same design principles at work, separated only by a mind-boggling difference in scale? To start, we don't have to look up at the heavens. We have to look down, and inward, at the blueprint for life inside every one of us. Building the case, Part 1: The scale of life. Before you can see the universe as a cell, you have to appreciate the cell as a universe. We tend to think of cells as simple little blobs. That's a gross understatement. A single cell, one of the roughly 37 trillion in your body, is a bustling metropolis of staggering complexity. Shrink down with me, past grains of sand, past bacteria, until you're at the edge of a single human cell. You're facing the cell membrane, a vast, flexible, and intelligent border. It's not a static wall. It's a security system with gates and sensors managing everything that comes and goes. Inside, you're in the cytoplasm, a thick, jelly-like substance that's more like a chaotic factory floor. Everywhere, there's activity. Ribosomes churn out proteins. The cytoskeleton acts as a highway system for transporting goods and provides the cell's structure. You'd see the mitochondria, the power plants, taking in nutrients and generating the energy that powers the whole city. They even have their own DNA, a relic from a time when they were separate organisms. And at the center of it all is the nucleus, a fortress containing the most precious treasure we know of, DNA. It's a library, a database with the information to build not just this one cell, but the entire organism. This single cell is a self-contained world. It has a power source, a transport network, a defense system, factories, and a central government. It's a universe in miniature. Now, zoom out. That cell is part of a tissue. Tissues form organs. Organs form you a walking, talking ecosystem of trillions of cells, all cooperating in a symphony of unbelievable complexity. This is the principle of emergence *. How complex systems and patterns arise from simple interactions. Think of an ant colony. One ant is simple. Thousands together exhibit a collective intelligence, a superorganism. Think of consciousness itself. It emerges from the interactions of billions of neurons. No single neuron is conscious, but together, they create the miracle of you. Life is an emergent property. The universe is a story of emergence. Simple particles form atoms, atoms form molecules, molecules form stars, and on at least one planet, those molecules formed cells. The principle is clear. Complexity builds on itself in layers. So, the question is, does this pattern stop with us? Or does it keep scaling up until the universe itself is revealed as the next layer? Building the Case, Part 2: The Cosmic Blueprint. To answer that, we now look up. For decades, astronomers have been mapping the large-scale structure of the universe. And as they plotted the positions of millions of galaxies, a breathtaking picture emerged. The universe isn't a random scattering of stuff. It's a vast, interconnected network. A cosmic web. Vast filaments of galaxies stretch across space like threads in a tapestry. Where they intersect, they form dense clusters. Between them lie immense, empty voids. The structure is intricate, beautiful, and eerily familiar. In 2020, a groundbreaking study made this familiarity startlingly real. An Italian astrophysicist, Franco Vazza, and a neurosurgeon, Alberto Felletti, did a rigorous comparison of two of the most complex systems in nature: the network of galaxies in the cosmic web and the network of neurons in the human brain. What they found went way beyond a simple visual resemblance. They took slices of the cosmic web and compared them to slices of the human brain, analyzing them with the same mathematical tools. One of these, a power spectrum analysis, measures how lumpy a structure is at different scales. The results were astonishing. Vazza stated, "Our analysis showed that the distribution of the fluctuation within the cerebellum neuronal network on a scale from 1 micrometer to 0.1 millimeter follows the same progression of the distribution of matter in the cosmic web, but, of course, on a larger scale that goes from 5 million to 500 million light-years. The way matter is clumping in your brain follows the same mathematical pattern as galaxies clumping across millions of light-years. The two systems, separated by 27 orders of magnitude in scale, share a similar design principle." They didn't stop there. They looked at network properties, like how many connections each node has. Again, the numbers lined up. As Dr. Felletti put it, structural parameters have identified unexpected agreement levels. He concluded the two networks likely evolved following similar physical principles, even though the forces gravity versus bioelectricity are completely different. The parallels kept stacking up. In both the brain and the cosmos, the active components, neurons and galaxies, make up only about 30% of the total mass energy. The other 70% is made of apparently passive components: water in the brain and dark energy in the universe. They even compared the memory capacity. The brain's is around 2 5 petabytes. The cosmic webs is estimated to be between 1 and 10 petabytes. The numbers are in the same ballpark. Now, Vasa and Feletti are not saying the universe is a giant brain. They're pointing to a mind-blowing case of convergent evolution. Two wildly different systems have self-organized into shockingly similar structures. It hints that there are universal laws of networks that work whether you're building with neurons or nebulae. This is our cosmic blueprint. The architecture of thought, it seems, is echoed in the architecture of the cosmos. The question is no longer if they look alike. The question is why. The climax, the universe as a cell. Let's take this clue and run with it. If the universe is a cell, what are its parts? The vast asterisk filaments of galaxies asterisk become the asterisk cytoskeleton. These aren't just threads. They're the structural framework of the universe cell, the highways that transport matter and energy, the cell's nutrients. The asterisk galaxies asterisk themselves are the asterisk organelles asterisk, each a specialized unit. A vibrant nebula, glowing with new stars, is like a asterisk ribosome asterisk, a factory assembling raw gas and dust into complex new structures. A stable, older galaxy could be a asterisk mitochondrion asterisk, a power plant steadily processing matter and releasing energy. And what about asterisk black holes? Smaller ones might be the cell's recycling centers, or asterisk lysosomes asterisk, breaking down old stars and matter. But the asterisk supermassive black holes asterisk at the heart of most galaxies could be the asterisk nucleus asterisk of each galactic organelle. Inside a cell's nucleus is the DNA. Perhaps the singularity of a supermassive black hole is the ultimate information storage device, encoding the laws of physics for our reality. This idea connects to a speculative area of physics known as black hole cosmology, which proposes our entire universe could be the interior of a black hole. This leads to the biggest question. What was the asterisk Big Bang? In the cell model, it transforms into something more natural: cell division. Mitosis. Imagine a parent universe reaches a certain size and replicates. Our Big Bang was simply the moment our universe cell pinched off from its parent to begin its own life. This replaces the awkward problem of a beginning from nothing with a potentially infinite cycle of cosmic birth, growth, and reproduction. Our universe isn't an orphan. It might have a family. This model even has a place for asterisk dark matter and dark energy. Remember how both the brane and universe are about 70% passive material? Perhaps dark matter, the invisible scaffolding holding galaxies together, is the asterisk cytoplasm asterisk of the universe cell. And dark energy, the force accelerating the expansion of space, might be the biological imperative to grow the cosmic equivalent of osmotic pressure. There it is. A complete, self-consistent picture. A universe not of dead space, but a living entity. Its structure mirrors life, its components have biological analogs, and its birth looks like a biological process. It's a metaphor, yes, but it's a metaphor the universe seems to be screaming at us. The implications. A conscious cosmos? If we entertain this, even for a moment, the implications are staggering. They shake the very foundation of how we see ourselves. First, if the universe is a cell, what is it a cell of? The answer is as terrifying as it is awe-inspiring. It must be part of a colossal, higher-dimensional being. We aren't just living in a universe. We are living inside a creature. Our entire cosmic existence could be a single metabolic cycle in one cell of a being whose nature is utterly beyond our comprehension. This brings us to consciousness. We see consciousness as an emergent property of our cells working together. This connects to a philosophical idea called panpsychism the belief that consciousness isn't unique to brains but is a fundamental feature of matter itself. Perhaps every system, from an electron to a galaxy, has some tiny flicker of inner experience. If the larger being is conscious, and the universe cell is part of it, then maybe consciousness truly exists at every scale. Our own awareness might be a small eddy in a cosmic ocean of consciousness. This also reframes the laws of physics. We struggle to unify general relativity, the very large, and quantum mechanics, the very small. But what if they aren't meant to be unified? What if physics is literally scale-dependent? The laws of relativity and quantum mechanics would be the local, intracellular, rules of our universe. The higher dimensional being would operate under a completely different set of physical laws, a trans-universal biology. We can no more grasp than a single neuron can grasp Shakespeare. The search for a single theory of everything might be a fool's errand if there isn't one set of laws. So where does this leave us? Tiny inhabitants of a dusty planet in an average galaxy. It could feel diminishing. Or, it can be profoundly empowering. It means we're connected to everything, not just metaphorically, but biologically. We are made of star stuff, but we're also part of the same living system as the stars. Our brief, conscious lives are part of a larger, cosmic consciousness. We aren't lonely observers looking out at a dead universe. We are the universe, looking back at itself. So, where does that leave us? We started by questioning the ghost of the simulation. We journeyed from digital code to biological chemistry. We dove into the universe of a single cell and found a blueprint for the cosmos. We looked at the cosmic web and heard an echo of the neural networks in our own heads. We've built a new story, one that transforms the universe from a machine into an organism, from a simulation into a cell. This isn't a proven theory. It's a shift in perspective, an invitation to look at the same stars and galaxies and see something new. To see a pattern not of bits and bytes, but of growth and metabolism. To see a universe that isn't just containing life, but as life. The parallels are just too striking to dismiss as mere coincidence. They demand we at least ask the question. In the end, we're suspended between two vast, unknowable possibilities. Are we ghosts in a machine, or are we thoughts in a cosmic mind? The truth might be something stranger still. But exploring the question changes us. It reminds us that the deepest mysteries are not just above us in the sky, but also within us. And so, we're left with one final, lingering question. If we are living inside a cosmic being, what does that being dream of? What are your thoughts? Is our universe a machine, an organism, or something else entirely? Let us know in the comments. And if you enjoy exploring the biggest questions out there, subscribe to join the conversation. The Big Bang was a transformation, not an explosion. You know the image. We all do. A single, infinitely dense point that explodes, creating the entire universe out of absolutely nothing. We've seen it 100 times in documentaries and textbooks. A violent, chaotic, singular event. The Big Bang. But what if that image is completely wrong? What if the Big Bang wasn't an explosion at all? A new wave of theories reimagines our origin story, not as a violent birth from a void, but as a profound and beautiful transformation within a reality that was already here. What if the universe didn't begin, but instead, it became? Stick with me, because this idea doesn't just tweak the details. It flips our entire cosmic origin story on its head, replacing the mystery of a creation from nothing with the mind-bending geometry of higher dimensions. The cracks in the standard story. Now, before we get ahead of ourselves, let's give the standard Big Bang model its due. It's one of the most successful theories in the history of science, and for good reason. It correctly predicts that the universe is expanding, with galaxies rushing away from each other like dots on an inflating balloon. It explains the existence of the cosmic microwave background, that faint, leftover glow of an early, hot, dense state that fills all of space. And it perfectly predicts the amounts of the lightest elements, like hydrogen and helium, that were cooked up in the universe's first few minutes. For all these reasons, the theory is a triumph. It's the bedrock of modern cosmology. But even the strongest bedrock can have cracks. And the Big Bang Theory has some deep, fundamental fissures that have left physicists feeling a bit unsatisfied for decades. The main problem, the one that keeps cosmologists up at night, is the very beginning itself. The singularity. The theory tells us that if we run the cosmic clock backward, all the matter and energy in our vast universe, every star, every galaxy, every planet gets squeezed into a smaller and smaller space. Keep rewinding, and you eventually hit a point of zero volume and infinite density. That's the singularity. It's not just a tiny, dense object. It's a point where our laws of physics, our very understanding of reality, simply break down. The equations that describe the universe spit out answers of infinity, which is a scientist's way of saying, we have no idea what's going on here. Think about what that implies. It asks us to accept that our entire universe, space and time included, burst forth from a point of no size, from literally nothing. It suggests a moment of creation that is, by its very definition, beyond the reach of scientific explanation. For a discipline built on cause and effect, this is the ultimate uncaused cause. As some physicists have half-jokingly put it, for all we know, dragons could have come flying out of the singularity. It's a placeholder for a mystery we haven't solved. And it's not the only crack. The Standard Model asks us to believe in other mysterious things to make the math work. To explain why the universe is so incredibly uniform on large scales, we have to add a period of cosmic inflation. An unbelievably fast expansion in the first sliver of a second, driven by a hypothetical energy field we've never seen. To explain why the expansion of the universe is speeding up today, we have to invoke dark energy, another invisible, unexplained force that makes up nearly 70% of the entire cosmos. These are like patches on a beautiful, but flawed, tapestry. They work, but they hint that we're missing a deeper, more elegant picture. The nagging dissatisfaction with something from nothing, and the reliance on these placeholders have pushed scientists to ask a daring question. What if the problem isn't the patches, but the fabric of the theory itself? What if the singularity isn't a beginning, but a misunderstanding? A universe within a universe. This is where the story gets really weird. Instead of trying to explain how the universe exploded from a point, a new set of theories asks, what if the Big Bang wasn't a birth, but a metamorphosis? Imagine our entire reality, all of space and time, is just a fragile membrane, or brane, for short, floating inside a vast, unseen, higher dimensional reality. A space often called the bulk. To get your head around this, let's use an analogy. Picture yourself as a two-dimensional being, a flat little stick figure living on a giant sheet of paper. Your entire world is just length and width. You have no concept of up or down. You can't even imagine it. Now, imagine that your sheet of paper is just one page in a library with an infinite number of other pages stacked above and below you. That immense, three-dimensional library is the bulk. You're living on a brane, a 2D slice of a 3D reality, totally unaware of the true scale of things. Theories based on this idea, known as brane cosmology, propose that our universe is in a similar spot. We experience 3 dimensions of space and 1 of time, but these might just be the dimensions of our particular brane, which is embedded in a bulk with 5, 10, or even more dimensions. This isn't just a fun thought experiment. It's rooted in some of the most advanced ideas in theoretical physics, like M-theory and superstring theory. These theories actually require extra dimensions to be mathematically consistent. For a long time, physicists just assumed these extra dimensions were curled up into a tiny, subatomic size, so small we could never see them. But brane cosmology offers a wilder possibility. What if at least one of these extra dimensions is huge, maybe even infinite? If that's true, it completely rewires the story of the Big Bang. The Bang is no longer an explosion that happened in space, it's an event that happened to space. It was the moment our brane came into being or went through a dramatic change within that higher dimensional bulk. Let's explore a couple of the leading ideas. One version is called the ekpyrotic universe, or the colliding branes model. In this scenario, our universe isn't the only one. The bulk is filled with many branes, floating parallel to each other like pages in a book. Every now and then, two of these branes might be drawn toward each other until they collide. The energy released in that collision would be immense, heating our brane to an incredible temperature and triggering a rapid expansion. From our perspective, living on one of the branes, this event would look exactly like a hot Big Bang. But it wasn't a creation from nothing. It was a collision within a pre-existing, higher dimensional space. This higher dimensional perspective offers a stunningly elegant solution to one of cosmology's biggest puzzles: the weakness of gravity. Out of the four fundamental forces of nature, gravity is ridiculously weaker than the others. A tiny refrigerator magnet can overcome the gravitational pull of the entire Earth to hold up your shopping list. Why? Brane theory has an answer. In this model, most particles and forces like photons, electrons, and the nuclear forces are stuck to our 3D brane, like flies on flypaper. But gravity is different. Gravity, according to these theories, is a property of the bulk itself. The graviton, the hypothetical particle that carries gravity, is free to wander through all the dimensions, on our brane and off it. This means the gravitational force we feel in our universe is just a tiny fraction of its total strength. Most of it leaks away into the vastness of the bulk. This leaky gravity would make it seem incredibly weak to us, trapped here on our brane, solving that long-standing mystery. Gravity isn't weak, it's just diluted across more dimensions than we can see. So, we have a new picture. The Big Bang wasn't a singular, explosive birth from a void. It was a transformational event, perhaps a collision between cosmic membranes within a larger, older, higher dimensional reality. This simple but profound shift in perspective doesn't just change the beginning. It changes everything. A new cosmic story. When you start to see the Big Bang as a transformation, a lot of the intellectual headaches of the standard model just dissolve. It gives us a richer, and you could argue, a more satisfying origin story. Let's start with the biggest problem: the singularity. In the brane world scenario, the singularity as we know it simply doesn't exist. There's no moment where the universe is born from a point of infinite density. Instead, the beginning of our expanding cosmos is the moment of a brane collision or the rebound from a previous phase of contraction. The laws of physics are never broken because there's no point where they need to be. The ultimate, uncaused cause is replaced by a physical mechanism, a collision, a bounce, a geometric shift. The question, what came before the Big Bang, is no longer a philosophical dead end. The answer is the bulk, a higher dimensional reality that was always there. This framework could also offer a more natural explanation for cosmic inflation. In some brane models, the energy that drives that initial rapid expansion comes directly from the physics of two branes colliding. You don't need to invent a mysterious, inflated field to get the job done. And then there's the question of why our universe is the way it is. Why 3 spatial dimensions? Why these particular laws of physics? Brane theory, combined with string theory, suggests a mind-bending answer called the string theory landscape. The idea is that the bulk might contain an almost unimaginable number of branes, perhaps 10 to the power of 500, or even vastly more, each with slightly different physical properties, each representing a different universe. Most of these universes might be sterile. Maybe they have 4 spatial dimensions, where stable planets can't exist. Maybe their forces have different strengths, so atoms never form. We, however, find ourselves in a universe with 3 dimensions and laws that are just right for stars, planets, and life, not because of a miracle, but because we couldn't exist anywhere else. It's a form of cosmic natural selection. We are living in one of the universes where the conditions happen to be right for observers to evolve and ask these questions. This completely reframes our place in the cosmos. We are no longer the result of a single, unique, and possibly inexplicable explosion. Instead, we might be a single note in a vast cosmic symphony. Our story changes from a sudden, lonely birth to an ongoing, transformative existence. Think of the metamorphosis of a caterpillar into a butterfly. Before the butterfly, there wasn't nothing. There was a caterpillar. It underwent a profound transformation to become something new. In the same way, the universe we see wasn't born from an explosion. It emerged from a prior state. The Big Bang was the moment of metamorphosis. It was the moment a timeless, uniform reality changed its form, allowing the complexity we see today, galaxies, stars, and us to crystallize. Our cosmic story is no longer about a birth, but about a asterisk becoming. Hunting for other dimensions. This is all a beautiful story. But is it science? Or is it just a fairy tale told with math? For any theory to be taken seriously, it has to make testable predictions. It has to point to evidence we can go out and look for. And remarkably, the theory of a higher dimensional universe does just that. First, to be clear, this new model doesn't throw out the successes of the standard Big Bang theory. The expansion of the universe, the cosmic microwave background, the abundances of light elements, all of these observations are still perfectly explained. A brane collision would create a hot, dense state that expands and cools, producing the same evidence we see today. The difference isn't in the what, but the how. The real excitement comes from the unique predictions that brane cosmology makes. If there are extra dimensions and gravity can leak into them, there should be subtle, telltale signs. One of the best places to look is at the Large Hadron Collider, LHC. The LHC smashes particles together at insane energies to recreate the conditions of the early universe. If extra dimensions are real, some very weird things might happen. For example, it might be possible to knock a particle so hard it gets ejected from our brane and flies off into the bulk. To us, that particle would just vanish, leaving an imbalance of energy in the detector. It would look like a violation of the law of conservation of energy, but it would actually be the first sign that there are more places for energy to go than we thought. The high luminosity LHC continues to search for such new physics. Another possibility is creating Kaluza-Klein particles. These would be heavier versions of familiar particles. The theory says they aren't new particles at all, but are familiar particles vibrating or moving in one of the extra dimensions. So far, no such signals have been found, but the hunt is very much on. Perhaps the most dramatic prediction is the potential to create microscopic black holes at the LHC. Normally, you need to crush a star to make a black hole. But if extra dimensions are real, they change the rules. It might be possible for colliding particles to get close enough for gravity to take over and form a tiny, fleeting black hole. These aren't cosmic monsters. They would evaporate almost instantly in a spectacular spray of particles. Finding such an event would be a game changer. As of today, none have been detected. The evidence might also come from the sky. The James Webb Space Telescope, JWST, has given us a stunning new window into the infant universe. One of its most surprising discoveries has been finding galaxies that seem far too large and mature to have formed so quickly after the Big Bang, according to our standard models. This impossible early galaxy problem has the cosmology community buzzing. While some analyses suggest these galaxies might not be quite as massive as they first appeared, a tension with standard models remains. Interestingly, some alternative theories, like those that arise from brane world scenarios, could potentially allow structures to form more rapidly, offering a possible explanation for what JWST is seeing. It's tantalizing, but far from conclusive. And finally, we're seeing brand new ideas emerge. On the absolute frontier of theoretical physics, some mathematicians are working with complex, seven-dimensional spaces called G2 manifolds. Highly speculative new theories propose that the properties of our universe, maybe even the masses of particles, don't come from the famous Higgs field, but from the pure geometry of these hidden dimensions. One bold paper even proposes a new particle born from the twistiness of this 7D space that could be the source of dark energy. This is physics at its most speculative and exciting edge, trying to unite the cosmos with particle physics through the language of pure geometry. Our place in the origami. So, where does this leave us? We're at a fascinating crossroads. The standard Big Bang model has been a brilliant guide, but we're now at the edge of the map, where "Here be dragons" is written. The puzzle of the singularity, the awkwardness of dark energy, and the surprising discoveries from JWST are all hints that our map is incomplete. The idea that the Big Bang was a transformation, not an explosion from nothing, offers a new and compelling direction. It reframes our universe as a brane, a slice of reality in a higher dimensional bulk. It replaces the problematic singularity with a physical event, a collision, a bounce, a geometric unfolding. It provides an elegant reason for gravity's weakness and a framework for a multiverse. It transforms our origin story from a violent, singular event into a moment of metamorphosis. We may not be the children of a chaotic explosion, but the current expression of a reality that is far older, grander, and more mysterious than we ever imagined. We could be living inside a piece of cosmic origami, and the laws of physics might just be the folds and creases of hidden dimensions. This is a profound shift in perspective. It suggests the answers to our deepest questions may not lie in finding a single moment of creation, but in understanding the enduring structure of the reality that contains us. The clues are out there, waiting in the debris of particle collisions, in the faint light from the universe's dawn, and in the subtle whispers of gravity. The search for them is the great adventure of 21st century physics. Exploring these ideas expands our sense of what's possible and deepens our wonder at the cosmos. If this journey has sparked your curiosity, make sure to hit that like button and subscribe for more explorations into the biggest questions in science. Let us know in the comments what you think. Is the Big Bang a birth, or is it a transformation? So, the next time you look up at the vast, dark canvas of the night sky, try to see it in a new light. Don't just picture the fading echo of a distant explosion. Instead, picture a cosmic metamorphosis. Picture a timeless, higher dimensional reality, once uniform, changing its form. Picture the moment it folded, or shattered, or collided, allowing a new and complex structure, our universe, to emerge. We aren't just looking out at the remnants of a beginning. We are looking out from within a single, beautiful, and intricate fold in the fabric of existence. And the greatest discovery may be that our universe isn't all there is. Our universe is a bubble, and it might collide with another. There's a baby picture of our universe. It's not a map of stars or galaxies, but a map of temperature, the oldest light there is, a faint glow of microwaves left over from the moment of creation. This is the cosmic microwave background, or CMB, and it's remarkably uniform. It's almost the exact same temperature everywhere, a perfect testament to a cosmos born in a blistering, homogeneous fireball. Almost. Because on this map, in the direction of the constellation Eridanus, there's something that shouldn't be there. It's a vast, unusually cold patch in the sky, a place where the universe is just a little bit darker and emptier. Scientists call it, simply, the cold spot. And it's not just a little chilly. it's about 70 microkelvin colder than the 2.7K average, a deviation that is statistically very unlikely. It's so enormous it would take 20 full moons to cover it in our night sky. For decades, cosmologists have been haunted by it. The odds of it appearing by random chance are estimated to be between 1 in 50 and 1 in 2000, depending on the models used, unlikely enough that it demands an explanation. For a long time, the leading suspect was a supervoid, a colossal emptiness in space, billions of light years across. And sure enough, surveys confirmed a huge void, the Eridanus supervoid, lies in that exact direction. But here's where the plot thickens. More recent, precise studies have come to a startling conclusion. The void is real, but it isn't empty enough to fully account for the intense cold. Depending on the analysis, it explains maybe 30 to 50% of the cooling, but a huge chunk of the mystery remains. This failure of our standard model to neatly explain away the cold spot forces us to the very edge of physics. It opens the door to ideas that sound like pure science fiction. What could be powerful enough to leave a bruise on our entire observable universe? The answer might be something that redefines not just our universe, but the very meaning of the word. The answer might be another universe. This cold spot could be the first tangible clue that we are not alone. It might be the scar from a cataclysmic collision between our universe and another. This isn't just a story. It's a mind-bending possibility rooted in one of the most bizarre areas of theoretical physics, brane cosmology. The idea that our entire universe, everything you've ever known, is nothing more than a bubble, floating in an unseen, higher-dimensional ocean. And in this ocean, there are other bubbles. And sometimes, bubbles collide. The architecture of the multiverse. So, how do you even begin to imagine one universe crashing into another? First, we have to totally rethink what our universe is. We're used to it being everything. The three-dimensional stage where all of existence plays out. But what if it's not? What if it's just a surface? This is the core idea that came out of the strange and deeply perplexing world of string theory. For decades, physicists have been chasing a theory of everything that can unite Einstein's general relativity, the theory of the very large, with quantum mechanics, the theory of the very small. The two theories are brilliant in their own realms, but at the heart of a black hole or the instant of the Big Bang, their math breaks down. String theory emerged as the most audacious candidate to solve this problem. It proposed that, at the most fundamental level, particles aren't dots. They're unimaginably tiny, one-dimensional loops of vibrating energy, strings. A string vibrating one way looks like an electron. Vibrating another way, it's a photon. All the particles and forces we see are just different notes played on these cosmic strings. It was a beautiful vision of cosmic unity, but it came with a huge catch. The math only worked if the universe had more dimensions than the three we see. Superstring theories, for example, require a total of 10 dimensions, 9 of space and 1 of time. M-theory, a deeper idea that unifies different string theories, operates in 11. So where are they? The theory's answer is just as wild. They're curled up, or compactified, on a scale so tiny we can't perceive them. Imagine a long garden hose. From far away, it looks like a one-dimensional line. But for an ant crawling on it, there are 2 dimensions, along the hose and around its circumference. String theory suggests we're like the distant observer, moving through 3 big dimensions, oblivious to the other 6 or 7 curled up at every single point in space. The specific shape of these hidden dimensions dictates the laws of physics in our universe. This is where the idea of a bubble universe starts to take shape. These extra dimensions led physicists to think about not just 1D strings, but 2D membranes, 3D volumes, and so on. They called these surfaces branes. And that led to a revolutionary thought. What if our entire three-dimensional universe is just one giant brane? In this model, all the stuff that makes us particles, light, the forces of nature are like open-ended strings with their ends stuck to our brane. We are trapped on this membrane. But this brane floats in a larger, higher dimensional space called the bulk. And in the bulk, there could be other branes. Parallel universes, each a distinct three-dimensional island, floating in a higher dimensional sea. But what if something could travel between them? In string theory, one thing might be able to. Gravity. Gravity isn't an open string stuck to our brane, it's a closed loop. And a closed loop has no ends to anchor it. It's free to travel off our brane and leak out into the bulk. And right there, you have a wild answer to one of physics' biggest headaches. The hierarchy problem. Why is gravity so ridiculously weak compared to the other forces? An ordinary fridge magnet can overpower the gravitational pull of the entire Earth. Brane cosmology says gravity isn't actually weak. We just feel a tiny, diluted fraction of its true power because most of it is leaking into the extra dimensions. This model doesn't just solve a lingering problem. It completely reframes our place in the cosmos. It implies our universe isn't alone. It's part of a multiverse. And if other branes exist, it begs the question, what happens if they touch? From beginning to another beginning? The ekpyrotic model, the Big Bang. It's the story we all know. But it leaves one nagging question. What happened before it? The standard model has no answer. The laws of physics break down at the singularity, so asking what came before is like asking what's north of the North Pole. But what if the Big Bang wasn't a beginning at all? What if it was just the fallout from a cosmic crash? This is the core of a competing idea called the ekpyrotic model, a name derived from the Greek word for a fiery rebirth. First proposed in 2001 by physicists like Paul Steinhardt and Neil Turok, it suggests our Big Bang was just the latest event in an endless cycle. Imagine two parallel branes, two universes existing in the higher dimensional bulk. For eons, a force slowly pulls them toward each other. As they drift closer, any wrinkles on their surfaces are smoothed out, which neatly explains why our universe appears so geometrically flat today. Then, after an unimaginable amount of time, they collide. This isn't two objects crashing in space. It is space, two entire realities impacting each other. The incredible kinetic energy of the collision is instantly converted into a firestorm of matter and radiation. That is our Big Bang. In this picture, the Big Bang isn't a creation from nothing. It's a moment of transformation. The universe was reborn from a cosmic impact. After the collision, the branes bounce off each other and recoil. The hot matter and energy trapped on our brane start to expand and cool the expansion we see today. Stars and galaxies form. Life emerges. But the story doesn't end. As our universe expands, the other brane moves away. Eventually, that faint, attractive force wins out again, and the two universes begin their long, slow journey back toward each other. The cycle repeats. A slow contraction, a cataclysmic collision, a fiery rebirth. A cosmic phoenix, dying and being reborn for eternity. This cyclic model is more than just a cool story. It makes different, testable predictions from standard inflation. For instance, while standard inflation should have created a background of primordial gravitational waves, the ekpyrotic model predicts they should be much weaker or absent. Future observatories might one day be able to detect these waves or their absence and tell us which story of our origin is true. The model replaces the inexplicable singularity with a physical mechanism. The question is no longer, what came before the Big Bang? But, what did the previous cycle of the universe look like? It transforms our origin from a singular miracle into a recurring, natural process. But if it's right, it means our universe was born from a collision. And if the cycle continues, it's destined to end in one. The collision, a cosmic reboot. We're used to thinking about cosmic collisions, galaxies merging, black holes crashing. But a collision with another asterisk universe? That's not an event in space. That's an event to space. It's the end of reality as we know it. Let's imagine it. On our brane, astronomers might detect strange gravitational effects on distant galaxies. Or maybe our detectors would pick up a weird, low-frequency hum that grows steadily louder, the sound of an approaching reality. But for most of us, life would go on, right up until the moment of contact. The collision would likely propagate through our universe at or near the speed of light. To us, it would appear as an expanding sphere, a bubble of new physics engulfing the old. Imagine looking up at the sky, and a patch of stars just blinks out of existence. Not blocked, but gone. Replaced by who knows what. The very laws of light and matter would be different inside the bubble. This bubble would expand outwards, devouring star systems and galaxies. There would be no warning. And then, it would hit you. The moment the boundary passes over you, you would cease to exist. Not dying, but being fundamentally rewritten. The atoms that make up your body are held together by finely tuned forces. Inside the new reality, those physical laws would be reset. What does that mean? The strength of electromagnetism could change. If it got slightly stronger, every atom in the universe would fly apart. If it got weaker, electrons would spiral into the nucleus. The speed of light could change. The strength of gravity could change. The new universe might be a chaotic sea of energy where stable structures like atoms are impossible. Or it could have laws even more conducive to complexity than our own. We can't know. From our perspective, it would be total, instantaneous annihilation. The boundary would sweep across the Earth in milliseconds, and our planet, our sun, our entire reality would be vaporized and repainted with a new design. This isn't a fender bender. It's a reboot of reality. If the ekpyrotic model is correct, this is the very mechanism that created us. We are the recycled debris of a former reality that was wiped out by a previous collision. It's a chilling thought. You can't build a shield against a change in the laws of physics. You can't outrun something moving at the speed of light. The end would be absolute. But in a strange way, it's also a beginning. The destruction of our universe would be the birth of a new one. Billions of years from now, in that new reality, perhaps new consciousness would arise, look at their sky, and wonder what came before, never knowing they were living in the ashes of our world. Is there any evidence? Revisiting the cold spot and other clues. Okay, parallel universes, cosmic collisions. It's an incredible story. But is there a shred of evidence for any of it? The hunt brings us back to the CMB cold spot. The conventional explanation is the Eridanus supervoid, a vast region with less matter that cools down the CMB light passing through it. The supervoid is definitely there, and this effect is real. But studies from projects like the Dark Energy Survey suggest it can only account for maybe 30 to 50% of the coldness. That leaves a huge part of the mystery unsolved. And when the main explanation has a hole that big, it lets more exotic ideas in the door. The most spectacular one? That the cold spot is a scar, a cosmic bruise left over from an ancient brush with another universe. While this is very much a minority view among cosmologists, the failure of the supervoid to fully explain the spot keeps the idea in play. Beyond the cold spot, the big hope is gravitational waves. The ekpyrotic collision model predicts a very different primordial gravitational wave background than the standard inflationary model. Inflation predicts a stronger signal, while a brane collision would produce a much weaker one. Our detectors aren't sensitive enough yet to make the measurement, but finding or not finding that specific signal could one day be a smoking gun. Then there's gravity itself. If brane theory is right about gravity leaking into extra dimensions, we might see its true strength at very small, sub-millimeter scales. So far, experiments testing gravity at these tiny distances haven't found any deviations, which puts limits on these theories, but the search continues. Finally, particle accelerators like the Large Hadron Collider are another long-shot testing ground. Incredibly high-energy collisions could, in theory, create particles that get knocked into the extra dimensions, vanishing from our perspective with a specific energy signature. No such events have ever been seen, but again, that helps constrain the possibilities. So for now, the evidence is tantalizing but speculative. Brane cosmology is a theory on the edge, but it's a scientific one. It makes concrete, falsifiable predictions. It tells us what to look for, and where. The philosopher's multiverse, implications and final thoughts. Thinking about this stuff really does a number on your brain. It feels like standing on the edge of a cliff. For centuries, humanity has gone through a series of cosmic demotions. We thought we were the center of everything. Then Copernicus told us we orbit the sun. Then Hubble showed us our sun is a nobody in a galaxy of billions, which is itself one of hundreds of billions. Brane cosmology is the ultimate demotion. It suggests our entire universe, in all its 13.8 billion-year glory, might be just one bubble in a cosmic foam. One sheet of paper in an infinite library. Our Big Bang might have been a totally commonplace event in a much grander reality. What does it mean to exist in such a cosmos? It means our reality is contingent. The laws of physics that allow us to exist might not be the only ones possible. It also fundamentally changes our perspective on beginnings and endings. The cyclic model replaces a linear story with a circular one. Our end is another's beginning. There is no final curtain, only the end of an act and the raising of the curtain on the next. This is a powerful concept, but it comes with a terrifying flip side. Our existence is fragile. We could be living on borrowed time, unknowingly drifting toward an appointment with oblivion. It's humbling, and honestly, a little unsettling. And yet, there's something incredible here. The very fact that we can even conceive of these ideas is a testament to the power of the human mind. From our tiny outpost, we are drawing maps of the entire multiverse. Brane cosmology may turn out to be incorrect. Maybe the cold spot is just a statistical fluke. But the value of a theory like this isn't just in being right. Its value lies in the questions it forces us to ask and the new paths of research it opens up. It pushes us to build better detectors and look at our data in new ways, hunting for the first crack in our current understanding. This is what science is all about, right? Pushing right to the edge of what we know and asking the biggest questions out there. If you love exploring these mind-bending ideas, do us a favor and subscribe and hit that notification bell. By joining this community, you help us continue to explore these incredible mysteries, from the heart of an atom to the edge of the multiverse. Ultimately, we don't know if our universe is a bubble. We don't know if other universes are floating just a short distance away in a dimension we can never touch. We don't know if a collision is in our future, or if our entire existence is the result of one in our past. What we do know is that the cosmos is far stranger, more vast, and more mysterious than we ever imagined. And theories like Brane cosmology give us a profound sense of wonder. They offer a glimpse into a reality so immense and complex it challenges our very definition of existence. Whether we are alone, singular creation, or one bubble in an endless cosmic foam, the quest to find out is the greatest adventure humanity has ever undertaken. The universe is under no obligation to make sense to us. Our privilege is simply to be here, for a brief moment, and get to wonder about it all. Our universe is a layer and we're at the bottom. You feel that, right? The solid ground under your feet. You experience time like a river, flowing forward, moment by moment, carrying you from what was to what will be. You see a world of 3 dimensions: length, width, and height, all held together by laws of physics that seem predictable, solid, fundamental. This is your reality. It feels real. But what if all of it? The ground, the flow of time, your own existence, is just a shadow? What if our entire 4-dimensional universe is just one of the bottom layers of reality, and events in dimensions far above us are pulling all the strings? The implications aren't just profound, they're chilling. What if the most basic things about our cosmos, from the force holding you to your chair to the very passage of your life, aren't fundamental at all, but are just echoes trickling down from a higher, unseen reality? Today, we're going on a journey to the very edge of theoretical physics, to a place where our universe isn't the whole picture anymore, but just a single page in an infinitely more complex book. We're going to explore the startling idea that we are living at the bottom of a cosmic hierarchy, a lower dimension subject to the whims of a greater, and perhaps terrifyingly different, existence. This isn't just a thought experiment. It's a possibility that grows out of the deepest and most perplexing questions in modern science. The first crack in reality's facade. To start this journey, we have to begin with a crack in what we think of as reality. And that crack comes from a deceptively simple question that has haunted physicists for over a century. Are there more dimensions than the 3 of space and 1 of time that we actually experience? The idea isn't new. It popped up back in the early 20th century, not as some wild speculation, but as a surprising result of math. A physicist named Theodor Kaluza was trying to unite the 2 forces they knew about back then: gravity and electromagnetism. He took Einstein's equations for general relativity and decided to see what would happen if he added a 5th dimension. Incredibly, the equations for light and electromagnetism just appeared, like magic. It was a stunning revelation. It suggested that gravity and light, which seem so different in our world, could just be 2 sides of the same coin geometry in a 5-dimensional universe. But that created an obvious problem. If this 5th dimension exists, where is it? Why can we only move forward, backward, left, right, up, down? Why can't we just take a step in that other direction? The answer, proposed by Oscar Klein, was as ingenious as it was strange. He suggested the extra dimension is there, but it's curled up into a circle so tiny we can never see it or move into it. Think about a garden hose. From far away, it looks like a 1-dimensional line. You can only really move along its length. But if you were a tiny ant walking on its surface, you'd find a 2nd dimension. You could walk around the hose's circumference. Klein's idea was that our universe is just like that. We're the giants who only see the long, stretched-out dimensions, while the extra one is a microscopic circle, far smaller than an atom, curled up at every single point in space. This idea, Kaluza-Klein theory, was fascinating but incomplete, and it lay dormant for decades. Then, it was brought back to life with a vengeance by the birth of string theory. String theory is probably our most ambitious attempt at a theory of everything. One single, elegant framework that can describe all the forces of nature, from the quantum chaos of tiny particles to the grand cosmic dance of galaxies. The core idea is actually pretty simple. If you could zoom in on any fundamental particle, like an electron, you wouldn't find a point. You'd find a tiny, 1-dimensional loop of vibrating energy, a string. According to the theory, everything in the universe, all matter, all forces, is made of these little vibrating strings. The different vibrations of a string create different particles, kind of like how different vibrations of a violin string produce different musical notes. An electron is a string vibrating one way. A photon is a string vibrating another way. A quark, another. The universe, from this point of view, is a cosmic symphony. But here's where it gets really weird, and where we get back to those hidden dimensions. The math behind string theory is incredibly strict. For the theory to actually work, to be consistent, it demands that the universe doesn't have just 4 dimensions. It requires 10. 9 of space and 1 of time. M-theory, an even grander framework that unites different versions of string theory, suggests an 11th dimension. Once again, physicists had to ask the same question as Kaluza and Klein. Where are they? And again, the answer was that they're hidden, compactified. Physicist Michio Kaku tells a great story to help visualize this. He suggests that at the very beginning, in the Big Bang, the universe was a perfect, 10-dimensional place. But this perfect state was unstable. It shattered. 6 of the 10 dimensions collapsed, curling up into a complex, intricate shape called a Calabi-Yau manifold. These dimensions are now so small, so tightly wound, that they're completely invisible to us. Our universe, the one we see, is made of the 4 dimensions that were left to expand and evolve. The existence of these extra dimensions, if they're real, has profound consequences. The specific shape of those hidden, curled-up dimensions isn't random. It dictates the physics of our 4-dimensional world. The way the strings can vibrate is determined by the shape of these extra dimensions. This, in turn, sets the properties of the particles we see: their masses, their charges, how they interact. The laws of nature, as we know them, are a direct consequence of the geometry of this hidden, higher-dimensional space. This is the first crack in our reality. The idea that the rules of our existence might not be unique to our universe, but are instead handed down by the shape of tiny, invisible dimensions we can never see. Our universe may just be one expression of a much richer, higher-dimensional reality. We're not seeing the full picture, just the projection of it on our limited, 4-dimensional stage. The whispers of weak gravity. If our universe's laws are just echoes from higher dimensions, we should be able to find some clues, right? Strange inconsistencies in our own world that hint at something bigger. Well, it turns out, there is a giant, glaring clue that has baffled physicists for decades. It's a mystery so profound it has its own name: the hierarchy problem. And it all boils down to one thing: gravity is ridiculously, inexplicably weak. You might not think gravity is weak. It holds planets in orbit and keeps you from floating into space. But compared to the other fundamental forces, gravity is an absolute lightweight. Think about this. Take a small refrigerator magnet. With that tiny magnet, you can pick up a paperclip, completely defying the gravitational pull of the entire planet Earth. A little piece of magnetized metal is easily overpowering the gravity of a 6 sextillion-ton sphere. The electromagnetic force in that magnet is something like 10 to the power of 36 times stronger than gravity. That's a 1 with 36 zeros after it. Why? Why is gravity so much weaker than all the other forces? This is the hierarchy problem. For a long time, nobody had a good explanation. But in the late 1990s, a revolutionary idea came along that offered a mind-bending solution, an idea that puts our universe squarely on a lower layer of reality. This idea is known as brane cosmology. Developed by physicists like Lisa Randall and Raman Sundram, and also by Nima Arkani-Hamd, Savas Dimopoulos, and Gia Diwali, the core idea is this. What if our 4-dimensional universe isn't all there is? What if it's a brane, short for membrane, a huge, 4-dimensional sheet floating inside a higher dimensional space called the bulk? Imagine reality is like a stack of paper. Each sheet is a universe, a brane. These branes exist inside a larger, higher dimensional space, the bulk, just like the sheets of paper exist in the 3-dimensional space of a room. Now, here's the crucial part. In these models, most of the stuff were made of the forces and particles of the standard model, like electromagnetism, quarks, electrons are all stuck to our brane. They're like ink on that sheet of paper. They can move around on the paper, but they can't leave it and float off into the room. But gravity, these theories suggest, is different. Gravity is not stuck on our brane. The particle that's thought to carry gravity, the graviton, is special. It can travel freely through all the dimensions, including the bulk. Suddenly, the weakness of gravity has a stunningly elegant explanation. Gravity isn't actually weak. On a fundamental level, it might be just as strong as the other forces. The reason it seems so weak to us, here on our brane, is that it's leaking. Most of gravity's strength is diluted because it's spreading out into those extra dimensions. While the force of a magnet is totally concentrated on our brane, the force of gravity is being shared across a much bigger, higher dimensional space. We only feel a tiny fraction of its true power. This idea comes in a few different flavors. In the ADD model, the extra dimensions are large, maybe even as big as a millimeter. That sounds huge, but since only gravity can get to them, we wouldn't have noticed. There are actually experiments trying to test this by looking for tiny changes to Newton's law of gravity at very small distances. In the Randall-Sundrum model, the setup is even more dramatic. They imagined a universe with two branes in a warped, five-dimensional spacetime. There's a gravity brane, where gravity is super strong, and a weak brane, which is our universe. Because the space between them is extremely curved or warped, gravity's influence gets exponentially weaker as it travels from the gravity brane to us. This warping naturally explains the enormous difference between the forces we see. And the implication here is just staggering. Our universe is not a self-contained system. It's a membrane floating in a higher dimensional reality. And the most fundamental force we know, the one that shapes the entire cosmos, isn't entirely from our universe. It's a visitor, a messenger from the bulk, and we only feel its faint whispers. This opens a Pandora's box of possibilities. Are there other branes floating out there? Could there be other universes parallel to our own, maybe just a millimeter away in a direction we can't even point to? The very weakness of the force holding you in your seat could be the strongest evidence yet that our reality is just one layer of many. The illusion of time's flow. So we've established that our laws of physics and even gravity might be dictated by higher dimensions. But what about something even more fundamental to how we experience life? What about time itself? We feel time as a river, flowing relentlessly in one direction, from a fixed past, through a fleeting present, into an open future. This flow seems like the most basic rhythm of existence. But from the perspective of a higher dimension, this entire experience could be a profound illusion. This idea comes from another pillar of modern physics, Einstein's theory of relativity. Relativity stitched space and time together into a single four-dimensional fabric called spacetime. A key takeaway from this is that there's no universal now. Whether two events happen at the same time is relative. It depends on how you're moving. This seemingly abstract concept leads to a radical rethinking of time, often called the block universe theory. The block universe theory suggests that if you take relativity to its logical conclusion, you have to accept that the past, present, and future aren't really distinct. They all exist simultaneously and are equally real. Imagine space-time as a loaf of bread. Each slice of the loaf is a moment in time. One slice is 1889, another is today, and another is the year 3045. In the block universe view, all the slices already exist. The entire loaf, the whole of spacetime from the Big Bang to the very end of the universe, is a single, static, four-dimensional block. From this perspective, the dinosaurs aren't gone. They're just located at a different coordinate in spacetime. Your birth, this moment right now, and every moment you will ever experience are all just different points in this block. The flow of time, that powerful feeling of moving from one moment to the next, is an illusion created by human consciousness. We're like a spotlight moving along a film strip. The entire movie already exists, but our consciousness only lights up one frame at a time, creating the illusion of movement. Now, let's take this one step further. What would this four-dimensional block universe look like to a hypothetical five-dimensional being? To them, our entire history could be perceived all at once, just like we can see a two-dimensional drawing in its entirety. They could see the beginning, middle, and end of your life as a single, complete object, a world line, stretching through space-time. They could see the whole history of the universe laid out like a map. For a being like that, our concepts of past, present, and future would be meaningless. The flow of time wouldn't exist. Everything that has happened, is happening, and will happen in our universe is just part of a static, unchanging object. Our experience of time passing is just a feature of our limited, four-dimensional perception. We are at the bottom, experiencing this block slice by slice. From above, the entire structure is visible and fixed. This has some deeply unsettling implications, especially for free will. If the future is already written, just as concrete as the past, are our choices really our own? If every event in your life is just a point on a pre-existing object, it suggests a universe that is completely deterministic. Your feeling of making a decision would just be your consciousness arriving at the point in space-time where that decision was always located. Now, this is where physics gets complicated and offers a possible escape. Quantum mechanics, the theory of the very small, seems to introduce a fundamental randomness into the universe. It suggests that outcomes aren't predetermined, but are based on true probability. This seems to clash with the fixed nature of the block universe. The debate over how to reconcile these two is fierce. Some think it means the block universe is wrong. Others turn to ideas like the many worlds theory, where the universe splits at every quantum choice, creating an infinitely branching tree of spacetime blocks. But even then, the perspective from a higher dimension remains profound. Whether our universe is a single block or a branching tree of blocks, a higher dimensional observer could potentially see the entire structure, all our possible pasts and all our potential futures. The chilling implication remains. Our most personal experience, the feeling of moving through time and shaping our own destiny, may be a product of our limited, lower dimensional viewpoint. We are prisoners of the present, unable to see the vast, static structure our lives are a part of. We are at the bottom, experiencing the illusion of flow, while from a higher layer, our entire existence is a frozen, timeless landscape. The architects of our existence? We've explored how our physical laws and even time might be artifacts of a higher dimensional reality. Now we get to the final, most chilling implication, where science meets an idea thousands of years old. What if not just the rules, but the very substance of our reality? Every star, every planet, every person is nothing more than a projection, a shadow cast by something more real in a dimension above. This is an idea the ancient Greek philosopher Plato famously explored in his allegory of the cave. Plato described prisoners chained inside a cave, facing a blank wall their whole lives. Behind them, a fire burns, and people walk by carrying things. The fire casts shadows of these objects onto the wall. For the prisoners, these flickering shadows are their entire reality. They give them names and study their movements, believing them to be real. They have no idea about the actual objects causing the shadows. Plato then imagines one prisoner being freed. He's forced to turn and see the fire and the real objects. The light hurts his eyes, he's confused. The real world is painful and disorienting. If he's then dragged out of the cave into the sunlight, he's blinded. But as his eyes adjust, he starts to see the true world: trees, animals, the sun. He realizes everything he ever knew was just a poor imitation, a shadow of a higher truth. For centuries, this was a powerful metaphor. But modern physics has given Plato's allegory a terrifyingly literal potential meaning. Could we be the prisoners in the cave? Is our entire four-dimensional universe just the wall where the shadows are playing out? Brane cosmology provides a framework where this could be literally true. If our universe is a 4D brane in a higher dimensional bulk, it's possible that the real physics and the real objects exist in the bulk. The particles and forces we see, stuck to our brane, could be the lower dimensional ends of more fundamental objects that stretch into the extra dimensions. They would be our universe's version of the shadows on the wall. Think about it like this. Your three-dimensional hand can cast a two-dimensional shadow on the ground. That shadow has its own properties: a shape, it moves, it can interact with other shadows. Someone living in a purely two-dimensional world might study that shadow and think it's a fundamental object. They'd develop laws of physics for how shadows behave. But they would be missing the entire third dimension. They would have no concept of your hand, the real object causing the shadow. Now, extend that analogy. What if a five-dimensional being could cast a shadow into our four-dimensional space-time? What we see as a particle, an electron, might just be the point where a higher dimensional string or object intersects with our brane. The life of that particle would just be the trace left by this higher dimensional object as it moves through the bulk. It's a thought so big it's hard to get your head around. It would mean that the fundamental building blocks of our reality are not fundamental at all. They're projections. It would mean that events happening in the higher dimensional bulk could have profound consequences for us, creating or destroying the shadows we see as particles and energy. Beings moving in the bulk could cause events in our universe that would seem random, causeless, and completely inexplicable: miracles or catastrophes appearing out of thin air. The laws of physics themselves might just be the rules of how these shadows interact on our wall. They'd feel fundamental to us, but they'd be entirely derivative, a consequence of the richer physics of the bulk. If the fire in Plato's cave were to change, the nature of the shadows would change instantly. In the same way, if the properties of the bulk spacetime were to shift, the fundamental laws of our universe could change in an instant. This leads to the ultimate humbling realization. We could be living in a derivative reality. We might be nothing more than the fleeting after effects of a higher, truer existence that we are fundamentally incapable of perceiving. We are at the bottom, not just in a spatial sense, but in a metaphysical one. Our existence is contingent, dependent on a reality we are blind to. We are the shadows, and the puppeteers are in another dimension entirely. The unseen scaffolding and cosmic mysteries. If our universe really is a lower dimensional layer, influenced by a higher dimensional bulk, then our cosmos should be full of mysteries, things that don't quite make sense in our four dimensions alone. And when we look out at the universe, that's exactly what we find. The two biggest puzzles in cosmology are dark matter and dark energy, and it's possible they're the best evidence we have for this unseen reality. Let's start with dark matter. When astronomers look at galaxies, they see a big problem. The visible stuff, stars, gas, dust, isn't nearly enough to explain the gravitational pull holding the galaxy together. Galaxies are spinning so fast they should fly apart. There has to be some extra, invisible mass providing the gravity to keep them intact. This missing mass is called dark matter. According to our best measurements, from missions like the Planck satellite, dark matter makes up about 26.8% of the universe. Ordinary matter, everything we've ever seen, is only about 4.9%. For decades, the leading idea has been that dark matter is some new type of particle we haven't found yet. Despite enormous efforts, we still haven't detected one. But brane world models offer a totally different explanation. What if dark matter isn't a new particle at all? What if it's the gravitational pull of things in other dimensions? In some of these theories, there could be another brane, a parallel universe, floating near our own. We could never see or touch the matter on that brane. But gravity can cross the void between them. We would feel the gravitational pull of the matter in that parallel universe, holding our own galaxies together, but we'd never be able to see its source. That invisible source of gravity would be exactly what we call dark matter. Dark matter could be the gravitational shadow of a parallel world. Then there's the even bigger mystery: dark energy. In the late 90s, astronomers discovered the expansion of the universe is accelerating. Some mysterious, anti-gravitational force is pushing space-time apart, faster and faster. This force is dark energy, and it's the dominant component of the cosmos, making up a staggering 68.3% of everything. We have no idea what dark energy is. The leading theory is that it's an intrinsic energy of empty space. But when physicists try to calculate how much energy empty space should have, their answer is wrong by up to 120 orders of magnitude. It's famously called the worst prediction in the history of physics. Once again, higher dimensions might offer a way out. Dark energy could be related to the interactions between our brane and the larger bulk. The repulsive force we see as dark energy could be a manifestation of energy stored in the bulk itself, or a subtle force between our brane and another. What makes this even more compelling is that recent data, looking back from early 2026, from projects like the Dark Energy Survey, DE, have shown growing tensions in our standard model of cosmology. While the model still holds up, data from DE and DESI have shown a mild preference for dark energy that evolves over time. Some analyses even suggest this acceleration could one day reverse, leading to a big crunch, where the universe collapses back in on itself, maybe in 20 billion years. This kind of dynamic behavior is hard to explain if dark energy is just a simple constant, but it could be a natural result of the dynamics of branes and extra dimensions. Now, it's really important to say that these ideas are speculative. String theory, after decades of work, has yet to make a single testable prediction that's been proven. But the theories persist because they tackle these deep problems in such a compelling way. They suggest that dark matter and dark energy aren't just extra things in our universe. They could be the telltale signs of the unseen scaffolding of reality, the evidence that our universe is just one layer in a much grander structure. We started this journey on the solid ground of everyday experience, a world of 3 dimensions, familiar laws, and steady time. We've traveled to the absolute boundaries of our understanding, to a place where that solid ground just gives way. We've seen how the very laws of physics might just be the geometric echoes of tiny, hidden dimensions. We've explored the idea that gravity seems weak only because its true strength is leaking into a higher dimensional bulk, and that our entire universe might be just one brane, floating in a vast hyperspace. We've confronted the possibility that our experience of time is an illusion, a product of our consciousness scanning across a static block of space-time that a higher being could see all at once. And finally, we have stood at the mouth of Plato's cave, stared at the flickering shadows, and had to ask the most terrifying question of all. Is our reality itself just a projection, an illusion cast by a truer existence in a dimension we can never touch? This is the ultimate implication of being at the bottom. It suggests our existence is contingent, shaped by a reality beyond our perception. The great unsolved mysteries of our time, dark matter, dark energy, the weakness of gravity, may not be problems within our universe, but signals from outside of it. This is all, for now, theoretical physics, a landscape of beautiful math and mind-bending ideas waiting for proof. But it's a vision of the cosmos that completely reframes our place in it. We may not be the masters of our own universe. We may just be the inhabitants of a lower layer, experiencing the trickled-down effects of a reality far stranger than we have ever imagined. So, where does that leave us? If we're on a lower layer, what's at the very top? What does this mean for consciousness? Is it, too, just a shadow? Or is it the one thing that can begin to understand the cave? The search for these answers continues. But the questions themselves change us. They force us to look up at the night sky not just as a window into our universe, but as a wall that might be hiding infinitely more. What do you think? Is our universe the ultimate reality, or are we living in a shadow world? Let me know in the comments. What part of this idea do you find most compelling, or most terrifying? And if you enjoyed this journey into the deepest questions of existence, be sure to subscribe. We have many more layers of reality to peel back together. Thanks for watching.